Good morning, everyone. Welcome to this CA Engineers webinar. There are still some people logging on. We have registrations of 65 people, although it'll probably be more because some of the larger organizations normally share their boardroom with a couple of people. I just want to express my thanks to the chief organizer, Tia, who's sitting across the desk from me. Thank you very much for diverting my attention. Yeah. Thank you very much for all the arrangements. And then also remotely, Marno van der Westhuizen is handling all the technical details. So we hope everything will run smoothly. I'd also like to thank Henk Reiker, I'm not sure if he's on today, for assisting with the getting people to present for the occasion today. And then thank you to the presenters for putting in a big effort to make these presentations. All the presentations will be made available to the participants with a link afterwards. Presentations will be in English as there are attendees who may not understand Afrikaans. Everyone, please mute your microphone and your camera, switch your camera off until you have something to say. I'd like to give you some idea how this webinar came about. I was involved in the CA group from the very early days, and we used to have 2 meetings annually in May and in November. The May meeting was specifically to discuss new equipment and technology, and the timing allowed participants to budget for items for the oncoming season. The November meeting was to view CA samples out of storage from research trials, and also to discuss CA research results. It was held at the ARC facilities where the industry, of course, donated some experimental chambers. And the event was usually followed by a sumptuous brine. So Anil, I hope you are listening carefully. Then when deregulation came, everyone decided to play their cards close to their chest, and the group dissipated. It must have taken 10 years when people realized that their competition was not their neighbor, but from overseas, and it was decided to reinstitute the CA meeting. But we started with the November meeting, and that proved to be very successful. Over time, I tested the waters regarding reinstituting a meeting in May. Although individual parties were interested, there didn't seem to be much enthusiasm. The Packhouse Action Group, under which the CA group falls, felt I should give it a go. So I was originally going to schedule one for May 2020, but of course, COVID intervened. In order to get some participation for this event today, I decided to get some interesting speakers, and the result in terms of the program as well as the turnout was totally beyond my expectations. The invitations were only sent to Poem Packhouses and also the members of the storage group, which of course are the technical people serving the industry. After the presentations, I'm going to ask the non-Packhouse people to leave the meeting so that the Packhouse people can then have a discussion on how they want to run this meeting in future, if they want to run it at all. But the November meeting this year is going to be combined with the post-harvest symposium. So the post-harvest, the Hort Grow symposium is normally run in the first week of June, but the post-harvest portion of that symposium has now been moved to November, together with the CA group presentations, and that will take place on the 23rd of November. So you can save that date, please. Good. I think we can move on to the first presentation. We have from Dr. Marius Heyshammer, and he's going to talk about moisture loss in packhouses. So Marius, if you can switch your camera and microphone on, please, and commence with your presentation.
Thanks, Richard. Can you hear me?
We can hear you.
Just good morning to everybody. I just want to say, Elke Kraus, Johan Strydom, Anel Boters, and Leon Taylor. I sent you all private messages, nobody answered. So I don't know whether the chat function is working on my computer. I'd also like to ensure everybody that I am wearing pants today. I hear that that's mandatory for Zoom meetings. So I've got my pants on this morning. And my presentation is 30 slides in 30 minutes. So it's going to be a bit of a low fly. I think most people have probably heard something similar from me before. And if not from me, then from somebody else. So yeah, without further ado, is my presentation showing here?
Yes.
Full screen, all go.
Yep.
Good.
Far away.
Okay, good stuff. Okay, so the presentation is about temperature and humidity interactions. I think we need to start with some physics because it underpins the fundamentals of management of moisture loss. So it's not a lot of stuff. It makes a lot of common sense. First of all, water molecules vibrate. They've got kinetic energy. All molecules vibrate, but specifically we're talking about water. The faster they vibrate, the higher the energy status, the greater the heat content, because heat is a form of energy. Secondly, we measure that energy status by measuring the temperature. So if you stick a thermometer into a fruit or into any object and you get a reading, that is basically a reflection of the amount of heat or energy in that object. Thirdly, water can exist in three forms or phases: solids, liquids, and gases. And then a change between one phase to the other requires a change in the energy status of the molecules. If we look at it more graphically, on the left, we've got a solid form of water in the form of ice. If we increase the energy level of the ice, in other words, we warm it up, it obviously melts, it becomes a liquid. If we add further energy to it, the liquid then evaporates into a gas. And then likewise, if we take the gas and we reduce the energy, decrease the energy, the gas or water vapor condenses back to a liquid. If we further reduce the energy level, it goes back to a solid. And everything inside this little green box forms the basis for mechanical refrigeration, for transpiration or moisture loss, and for condensation. So in mechanical refrigeration systems, we've got a refrigerant, not water, but a refrigerant, which is in a liquid phase. It absorbs energy at the evaporator, and it evaporates to a vapor. It then goes through to the condenser where it gives away energy and changes back to a liquid. So we've got the cycling taking place, and that basically is mechanical refrigeration. Okay, water has a unique characteristic amongst many molecules in the sense that it has van der Waals hydrogen bonds that pull these water molecules together because of the asymmetrical nature of the molecules. And there's a polar positive and negative, and these charges attract one another, so water is inclined to clump. Now, as the energy levels fluctuate in these water molecules, they either evaporate or condense. So in the system shown below, we've got liquid water in these dashes, water vapor in the form of these little circles. So if we increase the energy level of the liquid water, those molecules will start to vibrate faster because of the higher energy level. They start to break these hydrogen bonds between the molecules, and then you find evaporation taking place. So the liquid then evaporates to a vapor. Likewise, if we cool the water vapor, we take energy away, the van der Waals forces become more pronounced, and the molecules start to clump together, and you get condensation back to a liquid. So that phase change, this water vapor to liquid interaction, is a function of temperature largely. Pressure also plays a role, but in our scenario, post-harvest, we're basically talking about temperature. Okay, when the airspace above any liquid becomes saturated with water vapor, it no longer has capacity to hold water in the gaseous phase. And this is purely a function of the energy status. So any liquid at a higher temperature, will have more capacity to hold moisture in the form of vapor. At the lower temperature, as seen on the right, there's fewer water molecules in that given volume of space because of the lower energy levels and the fact that the capacity is simply not there to have that water in the vapor phase. Now, because it's a gas, as in any other gas in this atmosphere above the liquid phase, these water molecules exert a pressure, and we call that vapor pressure. And the more vapor there is in the system, the higher the vapor pressure. Now, any moisture loss that we're talking about in terms of fruit is driven by the vapor pressure deficit, which is the difference in vapor pressure between the fruit itself and the environment in which the fruit finds itself. So we're specifically looking at the inside of the fruit where we have fruit cells that are laden with water, and you've got intercellular air spaces, and those air spaces are totally saturated with moisture because we're working with fresh fruit. So in other words, we're looking at a situation where there's a 100% relative humidity in these intercellular air spaces. Because it's saturated, the vapor pressure is obviously very high. We know that the environment outside the fruit is very seldom at a very high relative humidity. In other words, the vapor pressure outside is normally much lower than inside. So we're sitting with a vapor pressure deficit, which is the difference between the high vapor pressure inside, the low vapor pressure outside, and that deficit drives moisture loss out of the fruit through any spaces that it finds, whether it be cuticular layers that are broken, diffusion through the cuticle, stomata or lenticels, any wounds, etc. So moisture will move purely because of diffusion, and this is the second law of thermodynamics that says you can't have a system where things are ordered and all the moisture is inside the fruit and nothing outside. Randomness must apply. In other words, there's purely a diffusion process that takes place because of the vapor pressure deficit. Okay, and if we look at this graphically, the vapor pressure deficit is linearly related to the rate of moisture loss. So if you double the vapor pressure deficit in any situation, you double the rate of moisture loss. And likewise, if we want to reduce the vapor pressure deficit, obviously we're reducing the rate of moisture loss, which is basically our main intent post-harvest in terms of maintaining quality, the lowest possible vapor pressure deficit to reduce the rate of moisture loss. Okay, now all of this can be related back to psychrometrics because we need a picture to see how this thing works and to be able to manage it and to predict certain circumstances. So a psychrometric chart, a simple format of which is shown here, basically looks at 5 factors related to moisture in air. It's the wet bulb temperature, dry bulb temperature, relative humidity, specific humidity, and then the water vapor pressure on the right-hand axis. If you have any of these 2 aspects or these factors quantified, you can deduce from this chart any of the other 3 that you don't know. And this is what we use the chart for. We measure certain factors, and then we deduce from the chart what these other factors, what the quantum of the other factors. Okay, let's just talk about humidity because it's sometimes a bit confusing for people. We tend to talk about humidity, and it's actually relative humidity, which is relevant to us, but there's also a humidity called specific or absolute humidity, which is also referred to as the mixing ratio. And that refers to the mass of water vapor per unit mass or per unit volume of air. And this is a specific amount. In other words, this is quantifiable in terms of you can take a certain volume of air, you can dry it out and weigh the amount of water that was in the air. That is a specific humidity. So looking at it graphically, you can see the temperature range along the bottom axis from 0 Celsius to 30, which is typically what we see post-harvest in the handling of fruit. And you can look at that temperature and the effect thereof on the absolute humidity at saturation level. In other words, when it's totally saturated, 100% relative humidity, which would by definition be the dew point, then you can see the green line represents the grams of water per cubic meter of air, and the red line represents the grams of water per kilogram of air. And they follow the same pattern. And basically what we see is as you increase the temperature from 0 up to 30, there's an exponential increase in the amount of moisture that's held either per kilogram of air or per cubic meter of air. And this is a very important factor because it's an exponential increase. The other humidity that we're always talking about, and which is relevant to our discussion today, is also the relative humidity. In this case, we are talking about a ratio. So this is something which is indicative of the degree of saturation of the air with moisture. So again, looking at the same temperatures, I've got the grams per cubic meter, green line that was on the previous graph. In other words, that's absolute humidity at saturation or 100% relative humidity line. If we take this little blue circle that's on the green line, so we see that at 10 degrees Celsius, there's that much moisture in the air. It happens to be 10 grams per cubic meter. And at maximum saturation, it's also 10 grams, so I am saturated. So 10 out of 10 is 100% relative humidity. The red circle just below it is not at 100% humidity because at 10 degrees Celsius, this has got about 7.5 grams of moisture per cubic meter of air. Maximally, what the air can hold at saturation is the 10 grams. So 7.5 out of 10 gives me a 75% degree of saturation or 75% relative humidity. Likewise, on the right, at 25 Celsius, saturation is about 24 grams per cubic meter. This specific sample down there is about 12 grams. In other words, we are half saturated, so we had 50% relative humidity. So that's what the relative humidity tells us. It doesn't tell us how much moisture is in the air. All it tells us is the degree of saturation of the air with moisture. So if it's 50% relative humidity, it means the air has the capacity to hold twice as much moisture as is currently present in the air. In other words, this sample, there can be twice as much moisture as what is present in the air at that specific time. Okay, just a quick example. If we harvest pears at 30 degrees Celsius, 30% humidity, we know that they're going to lose moisture. And it's driven by the vapor pressure deficit. And this chart allows us to quantify the extent of that, or the quantum of that vapor pressure deficit. So the 30 degrees Celsius is the fruit temperature. It's at 100% relative humidity, which is the topmost line. The reason why it's 100% humidity is because it's a fresh fruit. It's saturated with moisture internally. So in other words, we're looking at the vapor pressure inside the fruit in the intercellular air spaces, and that happens to be 43 millibars. The environment at the same temperature of 30 degrees Celsius, but only at 30% relative humidity, follow the line down to there, follow it across, we see it's 14 millibars of vapor pressure. So now we have a pressure deficit. Inside the fruit, the vapor is under 43 millibars of pressure. Outside the fruit, the vapor is only at 14 millibars of pressure. So there's a deficit and there's a driving force for moisture loss, which happens to be 43 minus 14, giving us 29 millibars of deficit. So this fruit is pumping moisture. We then put it in the cold room at 0 degrees Celsius, 90% humidity. It's still going to be losing moisture. The fruit has not changed temperature. It's just gone into the cold room. So the fruit is still hot. So it's still running at 43 millibars. But the environment has now changed. We're now in a cold room at 0 degrees Celsius with a relative humidity of 90%, the second line from the top. And if we look at it across to the right, that's 6.5 millibars of vapor pressure. In other words, what it's telling us, because the temperature is low in the cold room, even though the degree of saturation is 90%, it's still only 6.5 millibars of moisture or vapor pressure. So in other words, if you're looking at the specific humidity axis, which is over there, you can see that the amount of moisture in the air is actually very, very little. So the degree of saturation is high, but the absolute amount of moisture is very low. So cold room air is dry air. That's a fundamental principle. So now looking at the vapor pressure deficit, it's 43 less 6.5 gives us a 36.5 millibar deficit. So the situation for the fruit is actually worse than it was in the orchard. We went from a 29 millibar deficit to a 36 millibar deficit. So it's pumping out even faster. Obviously, the fruit will not stay at 30 degrees Celsius because you're in the cold room with air running around at 0. So obviously the fruit's going to cool down. So at the time that the fruit is cold, what is the situation? Cold room is still 0, 90% humidity. It's still 6.5 millibars of vapor pressure in the air in the cold room. The fruit is also now at 0, 100% humidity because it's a fresh fruit, which gives us a vapor pressure of 7 millibars, and that gives us a deficit of only half a millibar. And that's why we cool fruit. So to summarize that, in the orchard, we had a vapor pressure deficit of 29 millibars. Once in the cold room with warm fruit, the deficit increases to 36.5, but as the fruit cools down, that deficit rapidly drops And once the fruit is cold, we end up at a 0.5 millibar vapor pressure deficit. So the driving force for moisture loss, that vapor pressure deficit, is approximately 58 times higher in the warm fruit than it is in the cold fruit. And that's simply this 29 divided by half gives you 58. In practical terms, when you're talking to growers, it's easier to say that 1 hour in the orchard at that pressure deficit of 29 millibars is equivalent to 58 hours in the cold room with a very low vapor pressure deficit of 0.5 millibar. Or if you want to be even more practical, it's often not in the orchard for an hour, it could be 12 hours, and 12 orchard hours at that high temperature and low humidity is equivalent to 1 month in the cold room at the higher relative humidity and low temperature, where the vapor pressure deficit is only 0.5 millibar. So in other words, there's a lot of moisture loss taking place outside prior to it getting to the cold room, which I think the industry needs to address more urgently. Okay, so we recommend from the post-harvest side that the relative humidity in a cold room should run at 95%. And we know for a fact that many of the cold rooms are not at 95%, they're much lower. The shipping containers also vary tremendously. So what is the effect of a relative humidity of 80% versus 95% during the cooling and the storage of fruit? How bad is it to be at 80% rather than 95%? There's my fruit at 30 degrees Celsius. We know that the vapor pressure deficit is 43. If I cool that fruit in a cold room with an 80% relative humidity running at 0 Celsius, that's this scenario with the red line at 80% humidity is the third line from the top. So you've got to go down there, run it across. We see that the vapor pressure in the cold room is 5 millibars. So the fruit goes in during cooling, and it's a massive difference, 38 millibar pressure deficit that's driving moisture loss. If I have a cold room running at 95% humidity, which is the recommendation, the fruit is still going to be running up at 43 millibars, but now the cold room at a higher humidity of 95%, which is halfway between the 90 and the 100. So that's the one right over there. If we look at the vapor pressure on the right, we see that at 6 millibars, that gives me a deficit of 37. So the bad cold room has a vapor pressure deficit of 38. The good cold room is only 37. So there's, in absolute terms, a very small difference between the two. It's 1 millibar difference. So given the fact that it's for a short duration, this cooling that I'm talking about that's taking place now is going to happen within hours or days. In other words, the question is it really an issue if it's 80% versus 95%? If you're using a separate facility to do the forced air cooling of the product, separate to your storage facility, then in my opinion, the 80% humidity is not a bad thing. It's not good, but it's not the end of the world. However, if we're looking at it from a storage perspective, the system changes. Now the fruit is at 0 degrees Celsius, 100% humidity because it's already cold. And at the 80% relative humidity, we can see the fruit is running at 6.5. And with a poor cold room running at 80% humidity, we see that the vapor pressure in the air is 5 millibars, giving me a 1.5 millibar deficit. The good cold room running at 95% humidity has a vapor pressure of 6 millibars. The fruit is also going to be 6.5. So in other words, the vapor pressure deficit in the good cold room is only 0.5 millibar. Now one can say that the difference between 1.5 and 0.5 is still only 1 millibar difference. It's not a big deal in terms of in absolute terms, but we're talking about long-term storage. Then it becomes an issue. If you're going to have 3 times the vapor pressure deficit in the one situation versus the other, I would rather be at the 95% humidity for weeks or months than at the 80% relative humidity. So it is a big issue. Okay, looking at those, now the interaction between the temperature and the humidity against the rate of moisture loss or the vapor pressure deficit on this y-axis, looking at relative humidities anywhere from 70% up to 100%, because this is typically what we see either in cold rooms or in shipping containers. And we're looking at temperatures from 0 to 30 just to show the temperature effect. What we see at any given relative humidity, and I've just taken 75 as an example, we can see that obviously the lower the temperature, in this case 0 degrees Celsius is the bottom line, and 30 degrees is the top with increments of 5 degrees, we can see that as the temperature increases, obviously the vapor pressure deficit will increase or the rate of moisture loss will increase. I think the important thing to point out as well is look at the increment. That's a 5 degree increment with a fairly small increase in the rate of moisture loss. The topmost there from 25 to 30 is also only a 5-degree increment, but there's a massive difference in terms of the rate of moisture loss. And that's because of that exponential increase in the rate of moisture loss as the temperature increases. Looking at the effective temperature, and I've just chosen one at 20 degrees Celsius, what we see is as you increase your relative humidity from 70% towards 100%, there's a decrease in the rate of moisture loss. And we see this for all temperatures. It's more marked at the higher temperature than at the lower temperature, but they all show the same trend. It's a downward trend. As humidity increases, rate of moisture loss goes down. What I think we should be looking at, and this is something that the growers don't always want to see, is this part of the spectrum, because humidity doesn't start at 70% in the orchard. It's normally much lower, and it can be a lot lower than 25%. All you need to do is extrapolate this line backward. And you can see that at 30 degrees Celsius, which is not an unusual temperature for us in the Western Cape in summer when we harvest fruit, at that stage with a humidity of 25%, we have massive vapor pressure deficits, as I showed previously with the psychrometric chart. You can do the same for any temperature. In this case, I've done it for 20 degrees as well. And you can see that by just reducing the temperature from 30 to 20, in other words, from this line to this line, I've basically halved the rate of moisture loss. So some sort of effective pre-cooling in the orchard can make a massive difference in terms of the rate at which moisture is being driven from the fruit prior to it getting to the cold room. Okay, you don't have to use the psychrometric chart. There are many of these kinds of systems available on the internet where you can plug in values and then get answers from it. In this case, with this specific one, the website is given at the bottom. You plug in the temperature, the pressure, the humidity and the pressure, and then you can deduce all sorts of other factors. So in this case, I put in 0 degrees Celsius, 95% relative humidity with a pressure of 1,010 hectopascals, which is equivalent to millibars because I want to relate it back to that psychrometric chart. If you hit calculate after you've entered all those values, it gives you the mixing ratio or the massive water vapor per mass of dry air. In other words, in this case, at 0 Celsius, 95% relative humidity at that pressure, we have 3.6 grams per kilogram of air. Okay, if you want the saturated mixing ratio, that would be, had this relative humidity been 100% instead of 95, obviously the amount of moisture would be more, so that goes up to 3.79 grams per kilogram. It also gives you the dew point temperature, so you know anything below a temperature of 0.71 will get wet because of condensation. So this is a factor when we're talking about pre-cooling of fruit prior to packing. If you don't want to pack wet fruit because of the threat of decay, this is the sort of information that you would put in there, except that this would not be a cold room temperature and pressure or temperature and humidity. This would be your pack shed. It also shows you the absolute humidity in terms of grams of water per cubic meter of air. This was in kilogram on the left. This one is in grams per cubic meter. And then importantly, it gives you the water vapor pressure. In this case, specifically, the actual water vapor pressure at 0 Celsius, 95% relative humidity is 5.81 hectopascals. And the saturated one, which represents the fruit, because you're talking about saturated as 100% relative humidity, vapor pressure inside the fruit would be 6.11. So if you want to calculate the water vapor pressure deficit, it's simply a case of 6.11 minus 5.81. That would be the deficit driving moisture loss. So you can plug in any values you like up at the top, and you can find your water vapor pressure deficits right there. Okay, so going back to that other example with a temperature of 0 Celsius, 80% humidity, which is not great for the cold room, versus 0 Celsius, 95. The absolute humidity in grams per cubic meter, you get the two values there. And then obviously this is the 95 where we want to be. And then you can get systems where you say, fine, if my poor cold room is running at 3.88 grams per cubic meter of cold room space, and I actually want this good scenario of 4.61, the difference between the two is only 0.73 grams of water per cubic meter of cold room space. So yes, you can buy a humidifier and you can go and humidify the air by adding 0.73 grams of water for every cubic meter of cold room space, and that will raise your humidity from 80% to 95%. That's what you could do. The question, however, is why is this only 80% in the poor cold room? Is it a design fault from an engineer that didn't take into account the fact that you wanted 95%? Or did the engineer actually design the cold room properly to give you the 95%, but the client saved money by buying substandard equipment or smaller equipment, and then he basically buys himself a lower relative humidity, because that cost saving inevitably gives you this problem of a lower relative humidity. And in that situation, by humidifying the air, you're addressing the humidity issue, but you're also adding moisture that's going to condense on the coil. And at these sub-zero temperatures, the coil is obviously running at colder than zero. So in that case, any condensate will freeze, and then you run into problems with defrost and you lose temperature control. So it's, for me, a very poor second choice to start humidifying air. You should have the right design that gives you the 95% without any of these fancy additions. Okay, so looking at the effect of cooling, because in my opinion, this is the most important thing we can play with. The effect of cooling on VPD, this is for the stone fruit where we have basically a 5-week period from harvest till marketing. Obviously, at the time of harvest, your VPD is high. We've shown that around 29 millibars or whatever the case may be. It stays high until you get to the cold room. You put the fruit inside the cold room, the VPD spikes because your cold room environment is drier. Okay, so the VPD initially goes up very transiently, because as the product cools, the product temperature drops from 30 towards 0. You have a very rapid decline in the vapor pressure deficit until you get down to the level where your product is at 0, and you maintain a very low VPD for your export in the containers or whatever the case may be. That's the effect of temperature. If we look at the effect of cooling delays, because this happens, you have a certain protocol that says within a certain number of hours or whatever the case may be, I need to be at the cold room where I can experience the spike and the cooling. You can have a situation where there's a delay in the cooling, represented here by the red line. And in this case, all you're doing is you're pushing this line further out, you're maintaining the high VPD for longer. You then go through exactly the same spike as you would in the normal protocol. You have the same cooling rate as you would have in the normal protocol. You end up at the same level as the normal protocol, but this area between the blue line and the red line represents additional moisture loss that you've experienced in the fruit as a result of the fact that you prolonged this period at the high VPD. So all of this is due to the delay in cooling. Looking at the effect of the cooling rate, this is where the size of the system comes into play. Are you trying to cool a lot of fruit with a small system, or is it an adequately sized system? That would be the standard, the blue line. If you have a smaller system that's incapable of maintaining the correct temperatures or getting rid of that heat load, you have the red line, which just represents a much slower rate of cooling, which gives you that higher rate of moisture loss for a longer period of time. Then the difference between the blue and the red line, this whole area, represents the additional moisture loss that you would have because of the slow cooling and the slow reduction of that product's vapor pressure. So your VPD remains high because of the fact that your product is not cooling fast enough. Obviously, you can add a third line to this and say, let's have a green scenario. The fruit comes in, I've got a protocol that's improved, so I get it into the cold room faster. The spike is over there. I've got more rapid cooling, which drops it down faster. Then this area between the blue line and the green line would represent the amount of moisture loss that you've actually saved by improving your protocol and having efficient cooling. Okay, so obviously the size of the cooling system plays an important role. I'm not an engineer. I'm glad it's an engineer's webinar, so I'm sure there are many people listening to me now that are saying, okay, this is really simplistic, and it is. It's deliberately simplistic because I need to understand it. So what I'm showing at this stage is basically the thought process that goes into the design of a refrigeration system. And the size of the system in terms of the kilowatts required to do the job is a function of the heat load, which is the numerator in this little sum, and the cooling time, which is the denominator in this little sum. And these factors you can play against one another. And if you look at it, the size of the system is directly proportional to A, which is the pulp temperature, which makes sense. If I bring fruit in at a temperature of 20 degrees, I need a certain sized system to cool within a certain time. If the fruit comes in at 30 or 40 degrees, this numerator is a lot bigger. If my cooling time remains constant, then obviously dividing a bigger numerator by the same denominator is going to give me a much bigger requirement in terms of the kilowatts required. So that's the heat load is a lot bigger. The cooling time is the same, so obviously the system needs to be bigger. The other factors of importance there, obviously the air temperature, because the colder you want to deliver, the more impact that's going to have there. The mass of the product is important. If your cold room is designed for 20 tons, you can cool 30 tons, but it's going to take a lot longer because the heat load is 50% bigger. So that needs to be taken into consideration. And then the E at the bottom, the cooling time there is the 7/8 cooling time. That's the desired time. If you want to reduce this cooling time, which is what's happened now in the industry in the table grapes, they went from 72 hours to 48 hours as their protocol. And that's where they stuck now in terms of this little denominator has gone from 72 to 48. In other words, the numerator is being divided by a much smaller little figure, which means the system design needs to change. They need more kilowatts to do the same amount of work for the same heat load. So how can we manipulate that system? It's basically the same formula I've just shown you, and looking at the two scenarios. And this is where the table grape industry is now, where they are at the moment. They've got this existing capacity in many of their cold rooms designed for a certain heat load, for a certain cooling time. And what they've done now is they've said, okay, you need to cool faster. This cooling time has changed. So unless you change the heat load, it's impossible to maintain the same sized system and reduce the cooling time without messing with the numerator in this little sum. So the heat load needs to change. You either reduce the heat load by putting in less product, or you bring in cooler product. That's basically what you have to play with. If it's in terms of a new facility, obviously you can put in a larger system. So if you know what the heat load is going to be, you know what your cooling time is, you obviously can design to have a bigger system. At the moment you say bigger system, you're talking about a more expensive system. Bigger systems take more power, it's costly, etc., etc. But the point is we need to be honest with one another when we're talking about this. If you want to cool your fruit within a certain time, you need a certain size system. If you don't want to pay for it, live with the fact that you're going to have moisture loss, live with the fact that you're going to have claims. The analogy that I like to compare this with is pumping water out of a pool. So an Olympic-sized swimming pool with certain dimensions, with a certain capacity, 2.5 million liters. I can empty that swimming pool using a swimming pool pump. And that pump has a certain capacity. It can pump 12,500 liters per hour. So if I look at the total amount of water that I need to pump, divided by this capacity, it's going to take me 200 hours to empty the pool using the swimming pool pump. If I use an irrigation pump with a much larger capacity, it's going to obviously allow me to empty the pool a lot faster. And this is analogous to the cold room situation where I'm saying that this water in the pool represents the heat load. A cooling system is nothing other than a heat pump. It's pumping heat from the warm fruit to the cold air that we're circulating around the fruit. That cold air is transferring the heat that it's taken from the fruit to the refrigerant, and the refrigerant is transferring it in the condenser outside the system to the air outside the facility. So you're basically pumping heat from the fruit to the outside environment. So your heat load is this, represents this amount of water that I need to pump out of the pool, is the amount of heat I need to pump out of the fruit. With a small cooling system, with a small capacity, obviously my cooling time is going to be long. And with a bigger system, with a higher cooling capacity, obviously my cooling time will be less. But this pump, irrigation pump, is a lot more expensive than the swimming pool pump. And this is where the compromise comes in, where you need to decide together with your engineer, what are you going to afford to put in? It used to be standard practice, and I'm not sure whether it still is, that when those sums are made and the size of the system is determined, it used to be a case where in terms of putting in the system, it wasn't calculated at 100% of the requirement. It was calculated at 80% of the requirement. So in other words, they were deliberately putting in smaller systems, because the moment that your fruit starts to cool, you will be over capacity with a big pump, because the fruit is not going to be at 30 anymore. It's now going to be 29, 28, 27 very rapidly. And then your system is actually over-designed for the amount of heat that's in that cold room. So in order to save money, it used to be standard to slightly undercapacitate. Okay, so the bottom line with all of this, moisture loss is a physical phenomenon. It can be easily explained by physics. It's almost impossible to avoid, because there will always be a slight vapor pressure deficit. Your fruit will always be slightly warmer. There will always be air movement, etc., etc. Your humidity is never 100%. So in other words, we need to accept that it's going to be there, the moisture loss, but we need to manage its impact. Our primary tool is proper refrigeration. And I think this is where we really need to look at the systems that are out there and whether they're designed adequately. The handling protocols, in my opinion, are too lax. I think we're still allowing much too much time to cool the fruit, and that's causing more moisture loss than what is probably necessary. I think the last point, we are really not sensitive enough about adapting protocols to address heat waves, etc. I think we, as an industry, I think the fruit industry knows about putting in extra irrigation when they see the heat wave coming to ensure that the fruit is turgid, but I'm not sure that they actually manage the harvest any differently. The table grape industry, given the structure of their canopies, can harvest at night. If we get to the point where we now strip picking orchards, where you're not picking on color, etc., is it not possible to pick a lot of our deciduous fruit, I'm talking our pome and stone fruit, at night when it's cooler? I know it's not nice to get up early in the morning, but the table grape industry manages to do it, and I'm sure we could too. That's one way of getting past that problem of temperatures of reaching 35 or 40 degrees Celsius. Okay, this whole presentation has been about...
Maurice, 1 minute, please.
Yep, I'm done.
Okay.
This whole presentation has been about moisture loss, but if you look at the factors that impact on post-harvest quality, it's respiration, moisture loss, ethylene production, and decay all play a major role. And if you look at all of those factors and the effect of temperature on those factors, you see exactly the same situation. There's an exponential increase in the rate of respiration, moisture loss, ethylene production, and decay development as you increase temperature from 0 to 30. It's the same for all of them. In other words, reducing temperature from 30 towards 0, you get a massive reduction in all of these as well. So please don't see moisture loss as something on its own. It follows exactly the same process, or the same process as all these other factors. Thanks, Richard. I'm not sure whether there's time for questions, but if there are, I'm happy to entertain them.
Great. Thanks, Marius. Very important message. We did start slightly late, so I'm going to allow one question. If there's a pressing question, please unmute and ask your question. Okay, it doesn't look like it, so you can refer, for those who logged on a bit later, you can refer. Oh, Elke.
Sorry, I need to get used to Zoom. I'm more familiar with Teams. My things keep on disappearing. Maurice, I often get the question with chilling injury in apples or internal browning, depending on what kind of internal browning it is. Isn't it better to leave fruit outside overnight? So that's kind of a question that comes up a lot, and I would love for you to kind of say something about that.
Elke, I think it's one of those situations where you're weighing up two evils. So, if you're talking about apples and you're talking about Granny Smith or whatever, and moisture loss is not a major issue, then I see nothing wrong with doing it if it's going to give you better control of internal browning. You're not in that position, for example, when you're talking about browning of table grapes. You can't afford to leave table grapes outside overnight. So if your fruit is forgiving in the sense that you're going to be paying in terms of moisture loss, but gaining in terms of internal quality, and the gain exceeds the cost, then yes, by all means do it. But you need to prove that standing outside overnight is going to benefit you more than what it's going to cost you in terms of the moisture loss. In that sense, I wouldn't have a problem with it if that's the case, that it's actually going to benefit you more than it's going to cost.
I think also one needs to consider what the nighttime temperatures are.
Yes.
I don't think it's always that simple, because sometimes we also get things like greasiness if fruit is too warm for too long. So I think there are other things also to consider. So it's more controlled in a cold store. But if the temperature is low, I mean, anyway, so I don't think the answer is that simple. It's just one needs to check the conditions outside.
It's not that simple, and that's why I put that last graph in there to say that we shouldn't look at this in isolation. Moisture loss by itself, we can manage moisture loss. I mean, you can theoretically go and design a cold room to run at 100% humidity, you won't have any moisture loss. But you can have all sorts of other problems, because at 100% relative humidity, you are by definition at the dew point. And any temperature fluctuation will cause condensation, and condensation, we know, influences decay and all sorts of other things. So we can't see this in isolation and look at it purely from a moisture loss perspective. You've got to take all these other factors into account as well. But the psychrometrics allow you, if you've got good weather predictions, or it's a semi-controlled outside, where you've got some sort of control over air movement, etc., you can use the psychrometric chart and go and define for yourself what are the conditions going to be, and you'll see what the vapor pressure deficits will be, and you can predict the moisture loss.
Yeah, thank you. Thanks, Marius.
Good. Thanks for that question, Elke. Thank you, Marius, for a very interesting presentation, a good food for thought. For those who did log on a bit later, the presentations will be made available by a link, so you can refer back to the presentation. Good. Let's move on to the next presentation. It is about the Packhouse Action Group water benchmarking phase 3 results by Dianca Aesel of Blue North.
Thanks, Richard. Good morning, everyone.
Dianca.
Thank you very much. Let me just quickly share my screen. There we go. I can confirm I'm also wearing pants. Okay. Right. Yeah, you can probably all see my presentation. Let me just make it big here. There we go. All right. So for those of you who don't know me, my name is Dianca Aesel and I work for Blue North Sustainability. And I was the project manager for phase 3 of the Packhouse Action Group water benchmarking project, which we ran last year between September and November. And I'm just going to quickly run through those results. So just in terms of the data collection, we have a Excel-based data collection tool, which we've been using in the previous 2 phases, but we did make some changes to the tool in phase 3. One of those changes was that we added a data quality indicator next to all of the data fields, where the participants could indicate if their data is accurately metered, if it's estimated by calculation, or if it's just pure estimation, just to give us an idea of the accuracy of the data. We also restructured our packline processes section, put it into its own tab, collected more detailed data in terms of tonnage of fruit handled, pre-sorted, and also packed. And then for phase 3, we had 21 packhouses who responded to the request for data, of which 10 ended up participating. And of those 10, that included the 4 packhouses who also participated in phases 1 and 2. We also had 3 more packhouses who showed an interest in the project and participating, but they felt that they didn't have, good quality data yet to be able to get value from the project. But they were in the process of getting meters in place and getting their record keeping up to speed. So they would like to participate in a future round of the project. And then 7 more packhouses declined to participate because they just simply felt they didn't have the data. There was another packhouse who initially said they wanted to participate, but they didn't respond again after multiple follow-ups. So all of the data sets for phase 3 runs from January to December 2019, and we collected and calculated data for packing line, cold storage, and ablutions, offices, and canteen. Okay, so just some more info on our process. We first trained our participants in terms of how to use the data collection tool. We sent that tool to them. They captured their data. We offered them support where we needed. And then there's a percentage check process that followed once they sent that data to us. And then we calculate the results and we draw up some graphs. And you'll now see the graphs. They all have 2 colored bars. So there's a blue bar and then there's those with the yellow bars. The blue bars are just indicating where it's basically accurate meter data. And the yellow bars are just where there was mainly estimations or calculations. And there are some notes below each of the graphs if you want to know more information on a specific value. I won't be going into detail in the notes, but please do stop me if you have a specific question. All right, so we'll start with the packing line. Here, of course, the flumes makes up the most of the water consumption. And you can see we only had 2 packhouses here who could provide us with accurate meter data, packhouse A and B, and the water consumption range was basically 264 to 663 liters per ton. Now moving on to the cold storage, where the cooling towers, of course, make up the most of the water consumption. Here we had a lot more metered accurate data sets, but there's quite a lot of variation here, ranging from 3 to 14 liters per ton day. And that variation is just an indicator that there's a lot more learning and improvements that can take place, especially in terms of water usage at the cold storage level. At our ablutions canteen and offices, we once again see we only had these 2 packhouses who could provide us with accurate meter data, and that range was 38 to 59 litres of water used per person per day. Okay, now moving on to our year-on-year comparisons, once again starting with the packing line. So we could actually, because we had 4 of the packhouses who participated in phases 1 and 2, in 3 again, we could now have 3 years worth of data, so we could see these trends start to emerge. And for the different sections in the packhouse, just look at packhouse A for comparison purposes, because they provided for each 3 phases the most accurate meter data. But you will see, like you can see here at the packing line, there does seem to be this kind of upward trend in terms of water consumption, which is, of course, what we do not want to see. And we cannot confirm what this trend is until we, or if this is actually an upwards trend, until we have much more packhouses with accurate, high quality data participating in the project. But one potential reason we thought could play a role here is that since the drought of 2017 was broken, those water restrictions were lifted, perhaps the packhouses became a bit more liberal in terms of their water use, which could be a reason as to why the water consumption went up. So this is just for the packing line, but you'll once again see, looking at packhouse A here, for comparison purposes, at the cold store level, there's also this upward trend emerging here. And then when we look at the ablutions canteen and offices, you can ignore the 2017 data set here. There was issues in terms of the data allocation, but just looking at 2018-19 for packhouse A, you once again do see this upward trend there. Okay, and then just overall, the packhouse benchmark, it does appear, if you look at this graph, that on average, it's about 1 cubic meter of water used per ton of fruit packed in the packhouse. Okay, so this is just the water usage profiles to give you an idea of where most of the water consumption lies within the packhouse. There's a lot of variation here because a lot of the packhouses, they didn't have sufficient record keeping or meterings in place, a lot of estimations, etc. But overall, you can see that kind of most of the water, it gets consumed at the pack line level, followed by the cold storage, and then about 10% of the water is usually used by ablutions canteens and offices. Okay, and just to conclude there, so some of the positives from phase 3 is that the number of packhouses that participated in phase 3 actually doubled since the previous 2 phases. And we also actually had some of the participants reaching out to connect with other packhouses in the study, to share information, and that's really positive. It just shows that they want to share information and help each other in terms of using their water much more efficiently. Hopefully we'll see more of this if we get future phases of the project. And then of course we could once again do year-on-year comparisons, and because we had now 3 years worth of data, you can see those trends starting to emerge. So hopefully we will see those trends much more clearer when more packhouses start participating with quality data in future phases. And we had increased awareness of the metering blind spots and data quality issues for the packhouses. And we also had overall increased awareness of the project. We posted about it on the Hortgrow website, and there was also an article in Farmers Weekly. The challenge just remains data quality. So yeah, hopefully this phase 3 has made packhouses more aware of the importance of metering and being able to specifically pinpoint where your water goes in the packhouse. And hopefully we will see that more quality data sets in future phases. Sorry about that. Yeah, and then we also had closeout meetings with all of the participants in March, where they gave us some quality feedback and suggestions on how we can improve the project, and especially the data collection tool. Some of the things that they mentioned, for example, was that we should make a split between the packing line and pre-sorter water consumption, and then also the water use in the cooling towers, the effect of weather there obviously also plays a role. So that's something we need to consider. And then we've also gotten requests to actually do this kind of project, the benchmarking for the electricity in the packhouses as well. So that is something we're considering if we do get another phase. But of course, the next phase, that electricity needs to be fall within the scope of the project. So if it does, then we will also be looking at electricity in the future phase. So yeah, that's very, very briefly the summary of phase 3, and hopefully we will get another round. If any of you are interested in having access to this data, you can just contact me, or if you even just want to maybe participate in future phases of the project, please email me, give me a call. And yeah, that's pretty much it from my side. Are there any questions from anyone?
Great, thanks, Bianca. It's a very important project for the industry, and the message is to measure is to know. So if you're not measuring, please put in water meters. And if you want to look at how you benchmark against other pack houses, then participate and you know who to contact, because the benchmarking does highlight inefficiencies which one may not be aware of. Are there any specific questions? Just unmute, please. Okay, it looks like everyone's happy. So thank you, Bianca, for your presentation.
Thanks, Richard.
Right, now we go on to our next presentation, and it's about gas-tight coatings for CA ULO rooms by Ellen Hoogesteiger from Netherlands. The company is Ripstyle. Ellen, if I've got your pronunciation wrong, please help me. So if you can just unmute and share your screen, please.
Hello, good morning. My name is Ellen Hoogesteiger. Am I understandable?
Yep, you're loud and clear. You just need to get your screen shared.
Perfect. So, my name is Ellen. I'm from the company Ripstyle. Ripstyle is a company from the Netherlands. It provides coatings for a wide variety of industries. I'm going to give you a short presentation about Ripstyle today. If you have any questions, please save them for the end or in the chat box, and I'll be happy to answer them. I'm going to use a PowerPoint and a short video today. So, welcome to Ripstyle. Let me see if I can get this full screen. Yeah.
Okay, we can see it clearly.
Perfect. So Ripstyle is an international manufacturer and supplier of professional coatings, as I said, for various industries. Basically, we started in the fruit industry about 50 years ago, and it has expanded to other industries such as mushroom industry, as well as food industry and bulk storage. Basically every type of industry that needs a gas-tight coating or a vapor-tight coating to seal the room. We're also installer of coating systems. So what we do is we produce these coatings and we apply these coatings, and we provide our coatings worldwide. Yeah, so we work for several major construction companies in the refrigeration and freezing sector. And our aim is to expand internationally while being locally present. Our products, the gas-tight finishing of controlled atmosphere as well as ultra-low oxygen rooms is one of the most important activities of Ripstyle. Apart from that, Ripstyle provides vapor-tight coatings for the mushroom industry. It seals the mushroom growing rooms, the joint, and compost tunnels. It had also expanded to delivering industrial floor coatings and protective coatings. It's basically to be able to provide the customer with a complete solution. So if a fruit grower has a problem with its floor or with the floor beneath the door, or maybe some corrosion on some construction, we're able to provide a complete solution for their company. Characteristic for us has always been quality. We use a multi-layer technique, including a reinforcement layer, and the combination of these layers into a system provides the customer with a long-term solution. So that is very important for us to provide the fruit grower, for example, with a long-term solution, so he doesn't have to do maintenance every year. So getting more in depth about the gas tight coatings. When constructing a gas controlled atmosphere room, it's usually done by panels. It used to be done by sprayed polyurethane. And one thing that the room cannot function without is the gas tight coating, because when the room is not gas tight, it can have a leakage of air or an entrance of oxygen. Basically, it's not possible to completely control the room, and that is why we have developed our gas tight coating. It was about half a century ago. The first owner of Ripstyle was producing coatings for the maritime industry, and in that time, in the 70s, a lot of fruit storage, controlled atmosphere storages were built, and he was asked to produce a coating that could make the room gas tight, and it turned out to be a good move, and it has expanded since then. And now we provide worldwide controlled atmosphere rooms with our gas tight coatings. These gas tight coatings, they can be applied in cold rooms, controlled atmosphere rooms, such as ultra low oxygen or DCA rooms, but also ripening rooms or treatment rooms, for example, for persimmons or kakis, as well as storage rooms where rice or cocoa or seeds are stored, and where the humidity or the atmosphere needs to be controlled. So the gas tight coatings, they provide a gas tight seal on the joints and the corners, so that no air or oxygen can pass through and that the room can be completely controlled. But they also provide a hygienic finishing. So the room stays food safe, it's easy to clean, and it's a good base to store your fruit. So the properties of this gas tight coating is that it has a high gas tightness. It means that it provides a good seal in which air cannot pass through. They're also highly elastic. So our rip fill control coat, it is our main gas tight coating. It has an elasticity of 400%, and it means that it can move with the panels. So the panels are made of, I'm not sure what the name is in English, but the building can always move. And if the floor has a good base, then it's of course less, but the building never really stands still. And it needs to have that seal that can move with the room, so that when it's a long-term storage, that it keeps its gas tightness as well. So I've told you about the hygienic finish. It means that it stays white and clean during the years, because there's also fruit that you store maybe not at a very low temperature, but for example, there are some apples that you store at a temperature of about 4 or 5 degrees and Celsius, I mean, and then it's more easy to get, for example, some dirt on the walls. And our coating, it gives it protection to not have this adhesion of dirt on the walls. Besides that, it's durable and flexible. So it means that it's wear resistant. Of course, you always have to be careful for your storage room when driving with the forklift, but it's also easy to repair. And most important for us to provide the gas tight coating is that it's low maintenance. We see sometimes in the market fruit growers using alternative products that can dry out easily, that can crack easily. They have to repair every year. but the season of emptying the cold rooms is getting shorter and shorter because the fruit has to be stored longer, and maintenance, it's always a bad time for it, or there's no time for it. As well as during the fruit storage, you need to control the environment completely. So you do not want to experience any cracks or leakages of air during the storage. So the long-term solution, it provides that the fruit growers, they don't have to worry about the storage, the condition of the storage, and they can keep themselves entertained with storing the fruit in the most optimal way. So what it means is that the cold rooms are easily kept in regime. It means that, for example, during the fruit storage, during the controlled atmosphere storage, that the nitrogen generator asks a lot of energy while it should maintain the same. And it's not desired when the fruit storage is leaking and air is entering, that you cannot store your fruit completely. It provides a lower energy consumption and also maintenance of the nitrogen generator. Basically, the process is in better and more secure control. Of course, it's always a closed environment, and you have to be careful with the CA storage, but not losing the air or the oxygen entering, it spares a lot of problems. For example, for the treatment of bananas, the ripening, or the CO2 treatment of persimmons, it means that there is no loss of it and the entrance of oxygen is prevented. The duration of CO2 injection or treatments such as ethylene can be shorter because it stays inside the room, which also provides a uniform treatment of the product that is inside. And control and security. So what we also see is that sometimes treatments are done in containers, which are sometimes not completely gas tight, and it can be unsafe, or it can be the quality of the fruit is not completely preserved. The gas tight coating is a part of a system. So our main coating is Ripfill Control Coat, supported by Ripfill Store Coat. These coatings can be applied by brush or by airless spraying machine, and they are always supported by a primer. So we have a primer for sandwich panels and a primer for concrete. There are some old rooms with a sprayed polyurethane. They do not need a primer, so there are some substrates that do not require a primer, but most of them do. And the primer, it creates the long-term adhesion. So when first applying the primer and then a first layer of coating, then usually the fleece, it's the band that you see on the picture, is applied to give a reinforcement to the system, and then it's topped off with another layer of coating. So this may seem like some steps to create the gas tight seal, but it's necessary to create the long-term adhesion, because you need that adhesion on the panel and on the concrete to be able to give it that long-term solution. And the gas tight coating, it has the elastic properties, the durable properties, and the hygienic finish. It's possible to ask our application team to come to your company and to apply the products for you, but it's also possible to just order the material, get the instruction, help from us, and apply it yourself. It's also possible to get a short instruction on your company and then apply it yourself. So that's a lot of possibilities. So yeah, you can always ask us for a lot of different ways to apply it to your storage room. About the application, it's always important to start with a sealant. We always recommend to use a rip seal sealant. The sealant prevents the enclosure of air underneath the gas tight seal. You can achieve the right layer thickness more easily. We do not recommend to use silicone sealant. It is used a lot, but it creates some contamination and a bad adhesion result. So we would always recommend to use a repaintable sealant, such as Rip Seal. Yeah, so the first step after the construction of the controlled atmosphere room is to apply the repaintable sealant on the joints. And then our gas tight system is applied. I'm going to show you a video as well, which hopefully makes it a little bit more clear. It's basically the primer, one layer of coating, the fleece, and another layer of coating, and you're finished. And yeah, everybody can learn this. It's not difficult, and yeah, you have to get that one-time investment, but then you will not have the maintenance every year. Yeah, we are trying to recommend you to not resort to any short-term methods, as it can take, yeah, it's a lot of effort, but it comes back every year, or the adhesion is not good, so that the tape, for example, comes loose. Sometimes there's not a good base, as the joints are not sealed in advance, and it's a lot of trouble when you're trying to store your fruit or ripen it or give it the CO2 treatment. And it's yeah, you have to worry about your fruit storage not being gas tight or not being hygienic. So that's what we would like to spare you. I'm going to show you the video. I hope it works. So first the primer is applied. And then it's coating is sprayed on top of it. This is embedded. So I hope that makes it a little bit more clear. Yeah, more easy to imagine. Yeah, so we have expanded through the years as yeah, we have been providing our solutions worldwide, and our headquarters is based in the Netherlands. We also have an establishment in India, Poland, North America, and Russia. So yeah, we are an international supplier, but yeah, we want to be locally present and help the fruit growers locally. So yeah, and yeah, quality is very important for us. We have some certificates with which we work. It's ISO 9001 and ISO 14001. Our coatings are mostly water-based, which means that they are environmentally friendly. So yeah, we're happy to expand our gas tight coatings worldwide. Yeah, why should you choose for Ripstyle? We have a long-term experience, which means that we can, yeah, we have a lot of experience with adhesion, with different situations, older fruit growing rooms, newer fruit growing rooms. Yeah, so we can always offer a custom solution. We have a lot of high quality products in our variety. We can support it with the right primer, and our coating has that long-term experience. So we can offer professional advice, whether it's by telephone or just a short technical question via email. We're always happy to help, and please don't hesitate to call us for the smallest question that you have. We're happy to send one of our engineers to apply the products. We have a lot of gas tight projects a year. So as said, we also do the vapor tight projects or the protective coatings, some floor coatings. But the gas tight coatings, it's a really big part of our company. We train our employees in a very careful way, so that the persons that you get at your company are qualified and know how to apply the products. Thank you for your attention. I hope that it was a little bit clear for you. Please don't hesitate to contact us, and if you have any questions, you're welcome to ask them now.
Good. Thank you, Ellen. Thank you for your presentation. I'd like to ask, are you considering any sort of presence in South Africa, or will that depend on how things develop over time?
I think it depends on how it's developing. So what I heard is that the last years, it hasn't always been easy with the water supply, so that it's a little bit finding the way, how it's going. But as I said, we do aim to be locally present, so that's definitely a thing that would pass the agenda.
Good, thank you. Are there any questions for Ellen? Please unmute if you do. I think obviously the presentation was very clear. So everyone is happy. Thank you, Ellen. Thank you very much for your presentation today.
Thank you.
Good. Let's continue with the program. We're on to the next presentation, which is Growing a Greener Future with Intelligent Energy Storage System by Andre Swart of Blue Nova Energy. So Andre, if you can please unmute and prepare yourself for the presentation.
There we go. Good morning, everyone. Just quick confirmation, can you see my screen?
Yes, we can.
Excellent. So yes, my name is Andre Swart and I'm from the company called Blue Nova Energy. And I'm just quickly going to give you a brief introduction into the Intelligent Energy Storage System so that you know what we are talking about, who Blue Nova is, and just a general background. Otherwise, the presentation is not necessarily going to make sense. And kicking off, I just want to thank the previous presenters as well. Love the topics. I can hear electricity, I can hear energy, I can hear constant cooling down the system, you know. So for me, it's just like I'm walking into a nice garden. Everything has been paved out for me so that I can just continue and tell you about what we as Blue Nova do. So we are a company established in 2015, July. We manufacture batteries. We produce more than 3 megawatt-hour batteries per month. We've got more than 7,500 installations in Southern Africa. We're part of the JSE listed Reunert Group. We are ISO 9001 compliant. And our focus is really to take over the market as standalone energy storage systems throughout Africa. That's in brief just who we are, who I am. I've got 12 years experience in the engineering sector working for Eskom. Then I moved into a PV for Skatex Solar. So as you can hear, I'm moving constantly into something different, but still providing and supporting the idea of economical growth and electricity. Just a quick on not making it a sales, but so that you know that there's other products also available from Blue Nova. We've got a high capacity, a high current battery packs from 2 kilowatt hour up to 62.5. This is basically for lodges. Then we've got the rack powers. They are in the telecom industry, used mainly telecom towers. Then we've got the MPS series. They are for, I would say it's the replacement for lead acid batteries, and we'll come back to them right at the end when we start talking about forklifts. They are small, compacted, tenting, 4x4 in camping. That is typically where you would want to use these batteries. And then we've got a compact power station just to ensure that we can go through the load shedding that's taking place in some of the towns more than in others. Quick plug and play. But then essentially what I want to talk about today is our ICE, the Intelligent Energy Storage System. What it basically is a 6-meter container. Nothing beautiful about it. I mean, I think it will fit into your environments perfectly. It's a 6-meter container. It's got a high voltage battery pack. It's got a battery management system, energy management system that we call the RMAC. It's got its natural cooling for the inverters, HVAC for the battery side. And this product comes with a fire suppression system and access control, because we are working in a high voltage environment. So safety is priority. And it's got a 10-year warranty. Just quick, it's got a DC room basically where the battery pack is, and then an AC room in which the inverter, fire suppression and your controls are fitted in. Just a quick view on the inside, and I'm not going to dwell too much on these things, but we are building our battery pack with 12.5 kilowatt hour modules, as you can see, and they are being fitted in basically in series. What we do is, in the end, we don't just have a product that's from the shelf. We listen to the client, we interact with the client and find out what's the specific need and requirement, and then we build according to your needs. It varies from 140 kilowatt hour small battery high voltage pack up to 1.2 megawatt hour in a 6-meter container, and thereafter you can start paralleling these containers as well. So what do you actually do with an ICE? What is it used for? Now, just to go through some of the terms, and hopefully I'm not going to bore you and that you're already quite familiar with batteries and how they can support you. The main applications would be load shifting. And here we are talking about arbitrage opportunities, and I'll explain it a little bit more. But basically what we are saying here is that you would charge your battery during the off-peak tariff times and discharge the battery again during the peak tariff times. Then second application is peak shaving, absolutely just looking at the demand charges that's on your electricity bill, and then just cutting that top portion where there's peaks, pump starting, you know, just those that's actually sitting on the system for a few seconds, maybe a minute or two, but in the end you are paying thousands of rands monthly just because of that excess that you are using. Then for the ICE, there's a power factor correction application or availability, and here we don't even touch on the battery capacity or make use of the battery itself. It's purely just playing with the leading and lagging currents in your inverter. Then also the normal one, the one that I think that most people, especially during load shedding, talk about is the backup power or power resilience, ensuring an additional power source is available in the event of power failures on the network. It's reliable and it's cost effective. And hopefully you guys know this already, and you're starting looking out for something that can assist to ensure that you are building your business accordingly. And then just the fifth one that I want to throw in here is PV self-consumption optimization. A lot of people are going into putting PV onto the storeroom, roofs, and with a little bit of oversizing this PV, you can actually start also storing that additional energy into your battery pack, and then again use it during the peak times or when load shedding is taking place. So there's a lot of opportunity in having this large scale battery available. Now, just a quick on the energy storage system can be charged, discharged, or charged, let's say, through the utility. It can be charged with a generator, wind or solar, and be discharged into residential. Here we're thinking about, let's say, just the gated communities, estates, in the commercial, industrial, and then obviously focusing on you guys today in the horticultural market as well. Now, saying growing a greener future with an ice, I actually like the fact that Bianca was talking from Blue North, and we are Blue Nova Energy. So maybe I should just say growing a greener future with blue. But just to support what I'm trying to say, yeah, I think a lot of times expectations is the root of all heartaches. You know it from a business environment, everyone is shouting, lower the cost, reduce the cost. We don't know how you're going to do it, but you have to do it. And then please also just go greener. Because with those two, we're going to be a win situation. But then on top of it, they're still throwing also in, please be resilient. Build your business in such a way that you are resilient going forward, so that there's nothing that can lower you down, stop you, halter you, for not in the end produce the product that you are. And these are the three topics that I want to take through the presentation to show you how ICE can provide a greener future in your industry. And I know you've got a green industry already, but let's put a little bit of blue in there and see how we can get to a resilient company in the end. The reality check, however, taking into account what is being expected from you, tariff increases. We're all sitting waiting for the 15% increase that's coming from Eskom. That's not talking about the municipality where you're getting your electricity from. They're going to go to 17, 18, and maybe even 20% increases. So it's going to hit the pocket. Load shedding, that's the other reality that's been faced, and I think last week or the week before, we've already started feeling it. And when you look at this graph, this is the Eskom week on production, basically. You can see starting here right at the top, 2017, going all the way to 2021. You can just see that Eskom can't supply what they've been supplying over the last couple of years. There isn't, the demand can just not be catched up with what Eskom is putting on the table. So what's going to happen? More and more unreliable supply. On the one side, it's good when there's load shedding taking place, at least you've been informed about it. But when you're sitting on a farmer scheme, and I know many of you guys are sitting on 11 or 22 kV networks as well, it's just, there's a power outage, there's a fault on the line and you're being affected. Together with load shedding, not necessarily knowing when they're coming, it's going to interrupt your business. And yes, it hurts and it makes it difficult to manage and to live up to the expectations that's being created or requested from you guys. So I'm hoping that we can find a solution. But where do we start? I liked when Richard was saying to measure is to know. Most of the time, being in the electricity environment, that's the place to start, but no one knows. I don't know what my consumption is. But luckily we can fall back on the electricity bill. So you have to go grab on those electricity bills and start analyzing them and go into the detail. Looking at this electricity bill from City Power, and this is a 2019, but they look all the same. It's basically, there's different categories, the one being energy charges, and that's for the consumption that you are using on a monthly basis. Now, looking specifically at the energy charges on this account, it is roughly 57% of the account. Now, of that 57%, I can tell you that we can already reduce with having the right size battery there, at least 45 to 55% of the energy charges, because purely due arbitrage, through the load shifting that the battery can do, you can start taking away that and make it a reduction on your account. Secondly, there's the reactive energy charges, and with an ICE through the power factor correction, up to 4% of your electricity bill can go down. It's again just playing with the leading and lagging factor currents through the inverter. And then lastly, the demand charges, and that's the one that I said that you're just cutting the peaks. Just ensuring when you're starting up the motors or pumps that you actually just, instead of taking the power from Eskom or the grid or the municipality, wherever you're getting your power, you shift it onto the battery so that it does not incur higher cost on a monthly basis. So those are the three aspects that through ICE, through an intelligent energy storage system, you can start reducing your cost. So I'm just like, we still want to reduce. How do we do it? And as I said previously as well, I think most of you guys have already come to the answer that, hey, I can put up PV. PV is cheap. That's now the solar, the modules onto the rooftops or into a plantation, wherever you've got a little bit of ground. And yes, that indeed is the right direction to go. But before we continue there, I just quickly want to say, if you go and look at the arbitrage opportunity, and that is when you are on a time of use tariff structure, these two circles indicating low demand season, which is now in the summer times from from September to May. You have to say it the right way around, from September to May. And the high demand season, which is then June to August. Now there's 9 months in the low demand side and 3 months in the high demand season. When you look at this, there's the 3 times, the peak in the week from 7 to 10, and then again from 6 to 8. Now just that, the pure peak tariff time is approximately 45 to 55% of your electricity bill consumption. Now, what we are proposing is purely to say that let's make use of this advantage that you are sitting with. If you go and look at your time tariff in these time of use times, you can see peak time, I'm paying R1.38 per kilowatt hour during summer, and in the winter, R4.23. The same for off-peak, which is the green, which is from 10 o'clock in the evening up until 6 o'clock in the morning. I pay roughly 70 cents in the winter. This brings the opportunity, and this is just based on the Rudolph Flex. You really have to drill into your own accounts, go and make sure on what tariffs you are, and then start with this analysis. But if I take this as the example, peak, off-peak, arbitrage opportunity, and not what I wrote there, it looks quite opportunity, not that opportunity there. You can make a saving of 73 cents in the summer, and in the winter, R3.54. Now, firstly, we as Blue Nova, we are really transparent in everything that we are doing. And I would tell you, when I look at this, it's not making sense at the moment. If you want to do arbitrage purely based on load shifting, because this money that you are saving is just at the moment too small. But at the same time, I'm going to tell you, with the next tariff increase, that's definitely starting to make sense. And most of the municipalities, most of the Eskom tariff structures should start making sense with this coming electricity tariff increase in June. So look out and let's start analyzing. But in the winter, I can already tell you what a beautiful saving you can make. And I'll do a small analysis later in the presentation as well, so that you can see what I'm talking about. But coming back to my PV, this is a typical load profile of one of our clients, just indicating here we've got the peak tariff times, the 3 hours in the morning, the 2 hours in the evening. Now, what's happening is Eskom, when you put in your PV, and this is just a very beautiful sunny day, you can see that the sun is coming up just at the end of the peak tariff times, and it's going down just before the peak tariff time starts again. Now, what does it mean? Well, it basically just means that you're not cutting the consumption during the peak tariff times. Yes, you are making a saving on your electricity, you're reducing the cost, you can be self-consumption, providing for yourself during a sunny day. And I have to say that again, a sunny day, because just remember, there's clouds and there's rain. PV is not 100% reliable. It's not always consistent. And this is the things that we are trying to also just enforce, saying that a battery can be reliable, it can be consistent. You are sitting in the driving seat, being able to manage when the battery needs to be charged, discharged. You are putting basically the ground rules down. In this argument here, I'm just trying to show you that the peaks are still then going to exist. You're still not going to achieve cutting 45 to 55 of your electricity consumption portion of your electricity bill by just installing PV. And this is just a quick summary cost reduction exercise that we had for a client. They were paying approximately 1.5 million a year. After applying an ICE into their system, the annual cost went down to 1 million, providing them with a saving of 550,000 Rand for the first year. And I'm saying it very clearly, in the first year. Remember, no escalations has taken place. Next year, these numbers will just be growing in savings, because when buying an ICE, it's a capex that you have once off. For 10 to 15 years, maybe even 20 years, you'll have now I can't remember my own word that I wanted to use, but it's not a dynamic number anymore. It's a static number that you're paying per kilowatt hour. And this will be obviously different for each and every consumer or client or company. And therefore, we from Blue Nova side make it a point to really get involved in understanding what it is that your requirements are, so that we can size the battery accordingly. When we are saying that you require 1 megawatt hour today, we want to ensure that in year 10, with the warranty period, that you still have 1 megawatt hour available. And that's partially what we do from our side. We analyze, we size, and we start installing. The break even on this specifically was 5 to 7 years, where the battery was basically paying for itself. ROI is 15% and up. And again, I'm just mentioning those numbers, but it's things that we have to look together, because each company has their own way of looking at the ROIs. And when we get the bean counters involved, it's sometimes getting a little bit more complex, and then I just want to stay an engineer. But in the end, it's starting making business sense for most companies to really install a battery that can not only provide them with cost reductions, but also to support a reliable supply going forward. In quick, going greener as well. We acknowledge the backup generators that most people have, that they already have in their systems, and it's also still playing a crucial part. It is a support to the network. We're just saying, do you really want to run a generator at and I think this is a really a low value that I've included here, but R6.50 per kilowatt hour, in which you can pay more than or less than R2 per kilowatt hours through a battery and making use of arbitrage. We are playing around with the 5 hours a day, and purely just looking at where exactly is the best electricity available at the best price, and then starting to optimize the network accordingly. I quickly just want to show you as well, we've got an RMAC, which is basically our remote monitoring and control. In this picture, and I hope it's clear to you guys, but it's basically a PV plant, 280 kilowatt peak. They've got a diesel generator, you've got the ICE, which is the battery, and then the load. Everything being monitored through our RMAC, and then you can also start going into each of them, into their parameters. Yeah, I'm going specifically into the battery, and you can run an optimal integrated system from anywhere in the world and start ensuring that you are running it at a cost-effective way as well. This is obviously also set up per client. Whatever is important, the dashboard we can fill, and there's a lot of entries that can still be put into there. If there's different diesel generators, switching on the diesel generator at a certain time, switching over or checking on the PV and what the yield is, everything is combined robust into one system. Then just to quickly also show what we've doing, we had our first exports into Namibia as well. And yeah, it's the reason for this was obviously it's an off-grid. I think they're about 150 kilometers from the closest point of supply if it was coming from Nampower. It's a lodge. They are about 250 kilometers from Windhoek, but they are self-generated with their PV plant, having a generator for standby and a battery pack. And this is the total setup that they have, and they will be running this at a cost of less than R2 per kilowatt hour for the next 15 years. Economically, it's making sense. And I hope you start seeing this opportunity as well. Then also just again, so a lot of places is going off grid, just not trusting the supply anymore, looking for reliability of supply. And yeah, I mean, it's quick and easy, plug and play, understanding your network and ensuring that you've got the right, let's say, components put together. Then just in the end, I hope that you can see that going blue is going to make you go greener. Recycling, reuse, and reduce. When we can drill into tractors, for instance, and here we're talking about crank batteries, we are looking into the electrical forklifts, a lot of lead acid gel batteries that needs to be replaced, going into a lithium ion because we are a lithium ion manufacturer. It's just providing you with a longer, efficient time, working time, the battery lasting longer. And in the end, we also know that the pivot is also one of those places where you can put up a small PV with a battery and you can have total supply loose from Eskom or municipalities that is unreliable at the moment. And I think that is bringing me to the end of my presentation. I hope that there was something new that you guys heard, that there's something interesting for you. Please feel free to contact me. And yeah, I would love to just hear what it is that's your electricity problems at the moment, or any feedback to find out how we can actually support you as well. As you can see, we've got a range of products as well, and lithium is the answer into the future. And it's definitely a key component to ensure that you can become a cost reduction, more reliable, greener company in the future. Thank you very much.
Thank you, Andre. Very well explained. Are there any questions? Maybe the smaller pack sheds are wondering a bit about the scalability. Is there something for everyone, even smaller operators?
Yeah, no, definitely. I mean, we start from a household. So if you are running your company from your house, we can support you through load shedding there. So we've got the smaller 1 kilowatt hour, 1.4 kilowatt hour solutions there. But then in a 6-meter container, and again, it does not necessarily need to be in a 6-meter container. If you've got a small room on your premises where you want us to build basically your high voltage battery pack and inverter, we can do that as well. The scalability on a high voltage battery pack starts around about 140 kilowatt hours, going up, endless, but in a 6-meter container at the moment, we are placing 1.2 megawatt hours. So just again, I think that's important, understanding the use. I've started analyzing some of you guys sitting around the tables, companies, and you are pulling a lot of electricity to ensure that your cooling rooms are running. I'm looking in the summer months at 5 megawatt hour. Now to run 5 megawatts per hour, if you need to do that for, let's say, load shedding that's 2.5 hours, you're looking at least 15 megawatt hours. So it's a big battery that you require.
Good. Are there any questions for Andre? Just mute if you do, or unmute.
Richard, I've got a question, but it's totally not related to electricity. I'm just wondering, if the life cycle of the battery is finished, what happens to all that lithium? Where does it go? Can it be recycled?
Oh, thank you very much. You always find out what you didn't say through your presentation, so thank you for that. Yeah, so lithium specifically, it's one of those 100% recyclable batteries or cells. Remember, a battery has been built with amounts of cells. Those cells can be dismantled, and everything in the battery is basically recyclable.
Thank you.
Maybe just at the moment, there's an opportunity because there's not that many recycle places in the world. So that's still something that, specifically just for batteries. But here you're talking about the normal scrap yards where you can take the aluminium, copper.
Great, thanks.
Good. Any more questions? Okay, doesn't look like it. I saw flashing on the screen, great presentation, thanks. So from my side as well, thank you very much for a very informative presentation. And I'm sure you'll get some feedback later.
Looking forward to that. Thank you very much again for the opportunity.
Okay, let's move on. We're on to the next presentation, which is the IE4 motor efficiency that turns into great savings by Martinus Schreef of Zest Wes Group. Martinus.
Good morning, everybody. Can you hear me?
Yes, we can hear you.
I've tried to start my video, but it seems that it doesn't want to work with me today. So I'm just going to go full screen, make sure everybody can see this. Is that it? Everybody can see clear?
I can see it. Thank you.
Okay, good morning, everybody. Thanks again for the opportunity just to come and share with you. Also, from an electrical point of view, I'll just talk to you about efficiencies, and we're just going to be talking about the electric motor efficiencies. I work for a company called WEG, and just a quick intro. Just wanted to tell you about the company. We're based in Brazil, a beautiful town called Jaraguá do Sul. The factory is under roof about 1 million square meters. We've got the latest designs in the market. We offer training. We've got the widest range. And then just to highlight out to you, the factory produces in around about 60,000 electric motors per day. So that is quite a large number of motors. Locally, if you wonder where the Zest wig comes from, the local company Zest is a South African company. It was founded by a gentleman with the name James Blakemore, 1980. So last year we celebrated our 40th birthday. Head office in Johannesburg. We've been in Cape Town for about 27 years. And in 2010, the global company WEG acquired us. We have about over 900 employees, 8 branches across South Africa. And we also have the title of the largest stockist of variable speed drives and motors in Africa. Today, I'll just talk about electric motors, which is a core part of our business. But if you look at the snapshot, it's not just electric motors, it's the whole power distribution, all the way up to power transformers, generators, biogas generators, overhead transmission lines, and that's sort of a quick snapshot. So, talking about energy efficiency, I think it's really a challenge, as I've seen in some of the slides this morning, that we're all facing. I've done some research on the internet, read some websites, see what some of the clever people have said. And if you look at the last 2 decades, and this excludes the COVID impact we've seen over the last 12 months, our energy consumption has increased by 50%. So looking at this, and the forecast of what guys globally look at, see we will have to double our generation by 2050 just to sort of keep up with the global demand. And not only that, also it puts a lot of pressure to reduce our energy consumption on everybody. We also know all about the CO2 emissions. And at the end of the day, all of this put together has got an impact on us on the environment. And I think this forum is so relevant as we're talking about also crops and the agricultural sector and the fruit. So I just wanted to share with you again, if we look at it maybe from a bigger footprint, and South Africa is not very far off from this, but we say that if you take domestic consumption out, 60% of electricity is used in the different industry segments. And if we then go and look on those different segments, we find that the workhorse in these segments is electric motors. And the electric motors make up 65% of that energy that's consumed by the different industries. If we put that all together, if we look at globally, your electric motor makes up for about 40% of all electricity that is generated. So I've looked at the motor and we've looked at the history, and we just looked within ourselves as WEG as a company, and we've looked at a motor, 45 kilowatt 4-pole electric motor. And you can see at the bottom here, when we started producing our first motors in 1960, the efficiency of those electric motors was around about 88%. And a 20-year jump to 1980, we can see the electric efficiency has only improved by about 1.5%. More and more companies actually started asking us from the 1990s, large end users, to sort of see, is there a way that we can manufacture electric motor that would require less energy? And you can see how the jump has just gone from 1990, where the efficiency was around about 90%, all the way up to 2016. And even look at 2021 today, where we've got a motor that we've developed, the IE6, which the efficiency is sitting at 97%. So I think if you look at this over the last 20 years, efficiency and has increased greatly. If you just look at the note I've made at the bottom, we said we have reduced 20% of the losses compared in a motor of the recent development in the last 5 years. So I would like just to share this as well and sort of say, why am I doing this presentation? We look at a global map and we can see all over the world over the last 10, 12 years, all of the countries sort of laid out legislation where they have put a law in place that governs people when they purchase electric motors that it needs to comply to minimum efficiency levels. And we can see in North America, Canada, those places they refer to the NEMA premium, or as I'll tell you more what we refer to nowadays to IE3. Europe, it's been law since 2009. You can also see places like China, and those places they've implemented these policies as well. In places like Australia, they've also in 2019 changed to IE3 standards. But the challenge is that if you look in Africa, there is no legislation at the moment sort of telling anybody or what are the minimum efficiencies required for electric motors to be installed. And yet we see it daily, weekly, we read in the newspaper, and as we see in my colleague's presentation this morning, that there is definitely a shortage of electricity in Africa. So I'm just going to go back for the people just to sort of say, how do we look at electric motors efficiency? Look at the output, and that is typically what we require in the shaft. Often people will say I have a pump or a fan that I need to turn. And from that, we will look at the electrical input, which will be 100 kilowatts. And we say there's about a 5 kilowatt losses. So if we say the output over the input, we get to a motor which gives a 95% efficiency. According to international standards, there's an IEC directive standard that was implemented in 2014. It says all electric motors that started direct online will stop at an efficiency level of class IE4. And from 2016, there was a standard that says even if it's operated by a variable speed drive, this would mean that there will be a level of an IE5 will be included. What does it mean for us locally? Well, it means the speed range would be from 2 to 8 volt. That covers a wide range of electric motor speeds, and up to 1,000 kilowatts, which generally fits into most industry applications. You can see what they've done with the efficiencies. They've kept it simple. IE1 would be a standard efficiency, IE2 high efficiency, and so forth, up until we get to IE5, which is ultra premium efficiency. So with the standard, there's also some very important aspects that we need to sort of take into consideration. I'd just like to highlight this for the people to understand this. This standard defines the way that the motor is tested and how the efficiency is measured. And as a manufacturer, you need to obligate to these specific test requirements. It also means that once the motor is manufactured, the motor's rated efficiency and IE standards need to be put on the nameplate. And also the efficiency levels in the standards are not subject to any local changes. I cannot take an electric motor that's got a specific rating and adapt it for South Africa and say now it's changed from IE2 or IE3. And again, I just sort of show you at the bottom the different efficiency and the different standards and classes that's currently available. So with testing methods, according to the standard, again, there's what we call a direct method, and there's also indirect method. For us, we like to use the indirect method, and we will actually go and measure all the losses individually. So the standard also calls, as I said earlier, that on a rating plate of the electric motor, we need to clearly state what is the efficiency class, and with that together, we also need to sort of indicate what the efficiencies would be at 100, 75, and at 50% load. That is also just to sort of show you, because we often know that electric motors don't always run at 100% load. Sometimes they are oversized, and also to ensure that that efficiency of that motor has got like a flat curve, which means if the motor should be running at half, 3/4, or full load, that you're still getting the benefit of the efficiency level that the motor is stated. This is further developed for us to sort of look into the market and just sort of see what is actually happening in the market. What is the real picture? So we took a motor as an example, and this was a 37 kilowatt 4-pole IE3 motor. And we looked at some of the nameplates that we've discovered that is available in the market. And I'd just like to make this, just everybody aware that when you look at a nameplate, there could be suspicious information on the nameplate. I've covered out all the names, so I'm not sort of making known to anybody any specific company, but I would like to make people aware of what is happening. And if you look at the nameplate on the left, you'll see at the top it says IE space 3 and refers to a spec. It's not a spec, it's a standard that we need to comply with. And on this motor on the left with the silver nameplate, we also see that the efficiency rating on this specific motor is stated at 91.2%. Although we actually go and look that according to the standards, a 91.2% efficiency is actually an IE1, or as we refer to, standard efficient motor. If we again look to the rating plate to the right, the darker side one, we can clearly see that information on there is not original equipment. We can see that the engraving on there is not exactly the way it should be. And also, interesting fact that came out from this nameplate is that the efficiency on this motor is rated at 93.9. And you'll see in my curves later that I'll share with you, this is exactly according to the IEC standard. So this is very odd that you'll find an electric motor made and it complies to the T with the efficiency rating at 100%. Something else that we also picked up is that if you look at the weight on these motors, the one on the left indicates a weight of 268 kilograms, the other one 301. And I went and took a picture of our own rating plate, and somehow our motor is rated at 388 kilograms. I think it's often said, and maybe I can just add this to it. It's always said, it's always what you put in, you get out. And that's also questioned us in terms of the weight on the competitive products that I share with you. If we look at the motor that we've launched here locally in South Africa. We've launched the IE4 motor like just more than a month ago. It's based on the same platform that we've been selling into the market for the last 41 years. It's an evolution in terms of the design. And this motor will be replacing the IE3 motor, which we've known as the top premium efficient motor line. And some of the ratings I just want to mention to you are not covered by the IE4. More of that information to share in my presentation, but it will cover all the frame sizes from 225 to 355 and 2.4 and 612 motors for now. So many people often ask me, Martinez, how do you improve the efficiency of electric motor? And it's simple. I'll start at the top. We've got to look internally at the motor. So while we first start, we first sort of look at the stator, and we say the joule losses in the stator makes up about 40% of the losses in a motor. And we say, well, one of the ways to reduce that losses is by adding additional copper into the windings. That means we also go for a double layer. And for us in electricity, as we know, the more copper you're in, the lower the resistance. And again, we look at the iron losses that we find inside the electric motor rotor, the rotating part of the electric motor. And again, we say, how do we improve that? The only way we can improve that is by looking at the iron losses, and that means that we improve the laminations that we use in the motor, and we try to use the highest grade of silicone steel design that we can use in the motor. And on top of that, we also thermally treat the rotor to make sure when this motor is running at optimal temperature that efficiencies in this rotor is at its peak. We also look at stray losses, and stray losses is often, as we refer to, the gear gap. That is the gap between the rotating part and the stationary part, the rotor and the stator. And we also try to minimize that gap to make sure that the magnetic field that's generated is at its highest. And then 5% losses are mainly due to mechanical losses. And this is basically where we've looked at the motor to sort of say, how can we improve the motor? Where can we improve the bearings on a motor that's already of a high quality, high standard? So one of the aspects we can improve a motor is by looking at the design of the fan, of the cooling fan that sits in the back of the motor. Again, if we also look at the last one is the Joule losses that you also have rotor again. And that we look at actually optimizing the shape and the design of the actual rotor bars and the short circuit rings that sit at the end of the rotor. So if we just look at where the biggest gain in losses is, we'll see that the Joule losses and the stator, the Joule losses in the rotor, and the Joule loss and the iron losses in the rotor, that equates for 85%. So there's not much more we can do on a motor, except that all the changes to make a motor more efficient would be on the inside. Just a quick overview. What makes this motor great is that it's VSD suitable. We see more and more applications where people are using variable speed drives to control the speed of applications, such as compressors, fans, conveyors, and these drain holes for humidization. Any humidity that builds up in the motor, there's a way that the water can escape. We've got a special, what we call a wet sealing arrangement. This wet sealing arrangement helps us also to obtain an IP66 degree of protection, which means the motor is totally protected against a water jet. And again, with our insulation system on the inside of the motor, we also have longevity that we can sort of guarantee with our motors. What are some of the benefits? I'd just like to sort of say to you, there's at least a 5-year warranty that comes with the motor. We have a whole network of pre-approved service providers. The motors can be repaired. Often people come to me and say, Martinez, is it possible to repair these motors? Yes, can be fully repaired. And back to its efficiency levels. We keep spares. We keep a large amount of spares stock locally to ensure that the motor will run. One of the few companies that WEG had a design that always meant that spares are all interchangeable. So if it would be that you've got an old motor that was purchased in the 1980s and you would need a spare part, that the parts are all interchangeable, all the critical dimensions are all the same. So this brings me to a question. What would be the running cost if I have a 100 kilowatt electric motor that I would start? It's connected to a 100 kilowatt load, and that would be running the motor for 1 year. I use a standard formula that takes in hours times a kilowatt. I've worked on a Megaflex tariff of around about 98 cents per kilowatt, and that was the rating that was published for 2020-2021. And then I went to look at this motor and say, well, this is an IE4 motor, so the rating on the efficiency of this motor was 96.3. And I'm not sure if anybody wants to guess, but after running this motor for exactly 1 year, that would be the cost that we'll have to pay the utility company to run one motor of 100 kilowatt power delivered on the shaft for 1 year. It gets more shocking. What would be the cost of such a motor if I would go and purchase a 110 kilowatt motor currently? And that would equate to an amount of 86,000 Rand. So the running cost, even of a motor that's not fully loaded, far exceeds what we actually look at the purchasing price of the motor. And that's why it's always the best advice to look at when purchasing a motor, to look at the highest efficiencies available. So carrying on a slide that I've just shared with you now, the actual running cost would be 891,000 for 1 year. The motor we know would be 86,000 Rand. We switch this motor on, we run it for 5 weeks. There's a quick indication, just in terms of energy consumed. Within 5 weeks, we're almost the same in terms of energy cost of what we purchased the motor. And what I did this year, we looked at that motor, and I looked at 10 years. Running that same motor for 10 years would bring us a consumption bill of 12.3 million. How did I base that on? If you look at the bottom of my presentation here, I worked on it conservatively, and I basically said that I worked on 10 years with a 7% energy increase per annum. So often I also get asked this question, and people say, Martinez, but let's look at running costs, capital costs. What about I need to buy the lowest motor? We have tight budgets. And then again, we look at it. I've looked at a standard motor, and remember, we still sell standard efficiency motors. And I've looked at our new IE4 motor, so the efficiency ratings are very close. So there's only a 2.2% efficiency saving. And then people would say to me, that's 2.2% is nothing. We're not really interested. But if we look at the running cost of that specific motor over 10 years, we'll see that the running cost, there will be a saving of 287,000 Rand over 10 years. Then again, I look back at the capital cost, because that's often where we nowadays focus. We always say we need to reduce our expenditure. And buying an IE1 versus an IE4, there was only a difference of 11,244 Rand when a motor was purchased. Then we took it a step further, and then we said, you know what? It's always good to compare brand new IE1 motor with a brand new IE4 motor that is of the latest design and the latest construction and of the highest efficiencies. But we went to look at a motor, same motor, 110 kilowatt 4-pole motor. And this motor was installed, it's still running. It was installed in 2002. So a typical electric motor has got a design life of around about 20 years. And we looked at that motor when it was designed. Efficiency on the motor was stated at 92%. We looked at the hours of the motor running per year, around about 7,300 hours per year. And then we've calculated based on efficiency and the power absorbed, we worked out that this is our annual consumption per year. And as you can see, even just going from the old, what we call motor, to a new IE1 standard efficiency motor, we can already see there's a benefit in energy consumption. In other words, less energy is consumed because of the newer motor with newer designs. There's already a saving. Then we went and worked at what you would pay for that motor. Okay, that would be my annual cost. There's no savings. There's no price of a new motor. Payback, will be no payback. And we said that's what it will cost to run that motor for 10 years. And then I did the comparison, really just by looking at the price of a new IE1 motor, IE2 motor, that has been around since the 1990s. We did in 2015, we changed from IE2 to IE3, and you can see the prices remained the same. We introduced a better motor into the industry at the same price level. And as I said about a month ago, we now have introduced the IE4 motor at the same price level as what we used to call IE2, high efficiency, premium, top premium efficiency. And then we sort of just did the payback. And people often ask me, Martinez, how long will it take payback? That would be 6 months. That would be 5 months. That would be around about 4 months that we're talking for payback by installing a new motor. Running the motor 10 years, we can already see the cost savings. If we install just a new motor, kind of an IE4 motor, what was interesting to me is just having a look at that, seeing that the savings on the motor, yeah, we paid with a savings here, if you look at this, about 14,000 Rand, 28, okay, so it was a 14,000 Rand I saved. If we look at the period over the 10-year period, there was almost a 200,000 Rand savings on energy consumption. Again, people sort of say to me, how does our efficiency values compare to the standards? And again, you can see the standards versus our motors. As a reputable supplier, we always ensure that our efficiency standards exceed or at least are in line with the minimum requirements. Look at the market. I've also had a few customers saying to me, Martinez, but we were happy with the IE3 efficiency. Why have we gone IE4? When we already said to the people, this is the efficiency levels that we've already achieved in terms of electric motor, in terms of our efficiency levels for IE3. We look at the IEC standard and we look at the WEG standard, and we can already see there's quite a substantial jump in efficiency levels. And we can see this from a 5.5 kilowatt motor at the bottom. We can look at our efficiency levels, and as examples that I've used, 45, 110, you can already see there is definitely a savings in terms of efficiency levels from the motors. This is just a slide that I would like to share with you, saying that when we did the design change from IE3 to IE4, we made sure that most of the performance data is on par with IE3 in terms of the actual RPM that the motor runs, what we call the synchronous speed of the motor. We would know, of course, exactly that if we would have installed a motor that's more efficient, the motor would have actually run faster. But then again, we know on any fan or pump application, as soon as we started running faster, we would actually consume more energy. I did a comparison on kilowatt sizes here, and we can see there's anything between a 1.7 all the way up to 0.7.2. Power factor, there's some slight changes in power factor as well. We've tried to keep it to minimum. The nominal currents, lock rotor currents, and again, we've really tried to sort of make sure that all the motors are interchangeable, frame size, mechanical, and electrical are suitable for the current market needs. Payback times, we saw that briefly in 2 slides again. Again, people would come and ask me and say, Martinez, what do we do in terms of payback? When will I get the money back on my investment? And what I've done is here, we've looked at ratings from about a 55 kilowatt to 355 kilowatt. And we've looked at hours, and we looked at the efficiency between a standard motor and an IE4. And again, doing the maths, we see from around about just over 6 months. If a motor runs for more than 6 months, we can see that we start getting a payback period here. So as we start getting closer to a full 12-month period where the motor runs 24 hours a day, you will definitely get a payback. And as you see, as we start reducing, but the cutoff is here around about 6 months. Just to cover the topic again of what are some of the features, a robust motor, we've got approved service network providers. The big benefit is that we've introduced the motor at the same price level as the previous motor, the previous IE3 motor. So there's no additional cost for you as a customer. The motor comes VSD ready, comes with premium grade silicone laminations, solid integrated feed, drain plug for easy maintenance. And as I said again, we only manufacture in the market that offer a 5-year guarantee in our W22 range of motors. So to conclude, I would like to just some of the following things. I've done a spreadsheet that I'd just like to share with you as well. But so replacement is relatively simple. If we just look at changing an old motor to a new motor, because we also have a certification for the South African Bureau of Standards, we made sure that all our motor mounting dimensions, the feet, shaft lengths, shaft diameters, everything is according to the local standards and regulations. So replacing a motor would not be that it would require any changes in your bases or couplings as such. Through exchanging existing motors, the energy savings motors, the energy cost will decrease. We've seen that, done that with many applications. As we've seen also in a lot of the newspapers and what has been published, we will see that the current cost for energy in South Africa will increase. I've mentioned before, premium LV motors are designed to run for 20 years plus. And this means that even if the saving is not significant today, it will be in some years to come. The possible problem is that I've put in, this is my own words, I think the possible problem we have is not the price of energy, but the lack of energy, and energy savings can avoid future load shedding if we can all work together. I just want to quickly show you a spreadsheet that I've done. I just want to pause it quickly before I go to the questions. I just want to go here and just go here quickly. Just be with me one sec. Can everybody see the spreadsheet that I've got here?
We can see it, Martinez.
Okay, cool. So I thought, let me just look at something that is relative to pack houses. So with some feedback that I've got from some of our clients, a typical size of electric motor would be a 0.75 kilowatt. So we typically be small little motors. And I've also been told that the range would be between 0.37 to 1.5 would make up the bulk, and there would be about 80 to 100 units in a pack-out. So I said, well, let's work on 80 units. I worked on the current tariff that I shared with you in my presentation, about R1.10 per kilowatt hour. I've worked on and saying, in pack-outs, we won't work more than 6 months. And I stand to be corrected on this. I said maybe 2 shifts, 6 months, maximum a year. The rest of the time, with pack-outs would not be in operation. And then I went and looked at these 2 motors at the efficiency rating. I looked at the IE3 would be 82.5%. And the standard efficiency would be 72.3%. So we see a big jump in efficiency. And what I basically did here is I calculated how much it will cost us to run that motor over that same period. So we can see the IE3 would cost us 232,000 Rand. IE1 would work 265, and the savings would be 32,000 Rand per year, just changing 80 of these motors in one pack-out. What would be the savings in 5 years? It will go to about 189,000 Rand. And if I look at a 10-year period, that would work to 454,000 Rand. I then went and did another little interesting example here that I just quickly did, and I said, what does it cost if you buy one of these motors from us? And that would be the net price. And I would look for the cheapest motor that we would sell, an IE1. And I said the difference is 700 Rand per unit. There's 80 of these motors we would like to replace. So the payback would be 57. And just looking at our savings that we would do in our first year and second year, I calculated the payback for these motors would be in 20 months. And like I said, straightforward. This is just the Excel spreadsheet that I used just by getting some numbers. I used the same formula. And then what was interesting, as the lady Andre just mentioned, I went to look at the compressor because, hey, pack-outs only work for a certain period, but we need to cool that pack-outs or the storage facility. And I worked on an average size of one 250 kilowatt motor, same tariff. I've worked on a motor working in 20 hours per day for a year. I look at efficiencies between the IE4 and IE1, and as we can again see, it's about 2.9%. And then I've calculated the savings for that motor in 1 year would be 63,000 Rand. Just over 63,000 Rand per year would be the savings. I've looked at what the savings will be over 5 years, and that would be 367,000 Rand. 10 years, talking about a saving of about 800. And then I did the same cost analysis again. I said, what would that motor cost us brand new? And that would be the net price. And what is my cheapest IE1 motor? I went and got a price on that one. And the difference would be 21,000 Rand. And I did a quick summary and I said, if that is the savings that we get per year, I worked it out in 4 months. So that motor will pay itself back in 4 months. I'm just going to go back to the presentation and just go back here. Any questions?
Good. Thanks, Martinez, for your presentation to educate us on the efficiencies and cost benefits of these motors. Are there any questions for Martinez? Just unmute if you do. Okay, doesn't look like it. So thank you, Martinez. Let's move on to the last presentation. And that is on CO2 scrubbing, sizing, room loading and efficiency by Josh Kreft of Gas at Site. So Josh, you
Morning,
can...
Richard.
By the way, morning.
Can you see me there?
Not yet. We can hear you.
Fantastic. I'm going to share my screen. And while I do that, Richard and Thea, thank you for organizing today's webinar. Great initiative. You can tell it's an engineer's webinar. We've been doing a lot of maths and we're talking a lot about efficiency and whatnot. So I hope I don't lose you with a bit more maths. Right, have you got my screen there?
Yes, yes, we can see your screen. Thank you.
Okay, fantastic. Hopefully when I'm done speaking today, I can have you all smiling at your scrubbers like Mr. De Jager over here. Okay, so in today's talk, we're gonna talk about the trend to lower carbon dioxide levels and how that may mean that you don't have enough installed scrubbing capacity. We'll talk about how using an average carbon dioxide level across your complex might not always be sufficient, and that if you're struggling with your carbon dioxide set points and to maintain them, we need to check the maths and also the efficiency of the carbon inside our scrubbers. So what is a carbon dioxide scrubber? A scrubber is filled with a specialized activated carbon, which absorbs CO2. The carbon, it's a porous adsorbent material, and the carbon dioxide molecules actually attach to the surface of this carbon. And your carbon inside your scrubber will saturate slowly during a cycle. And that's why our scrubbers have 2 drums and 2 blowers. And this enables us to regenerate 1 drum of carbon while we're scrubbing with the other drum. So we're continuously scrubbing the carbon dioxide out of your room. Okay, we all know that if something is rare, it means it's harder to find. But likewise, if we've got less carbon dioxide in our rooms, it means it's going to be harder to remove that carbon dioxide from our rooms. For that reason, we use this table and we learn how to apply a scrubbing factor to account for this difficulty to remove the less carbon dioxide that we've got in our room. So we'll use this table again later when we're doing our calculations. Here's our range of isocell scrubbers, and notice here Eco 850 how as the carbon dioxide level in the room drops, that's on the left hand side here, so does the ability of that scrubber to remove carbon dioxide from the room. So you'll notice that the scrubbers, the Eco 850 is a nameplate capacity. It's an Eco 850, which means it can remove 850 kilograms of carbon dioxide from the room, and that's always at 3%. So the nameplate of the scrubber is at 3%. And if we look at the scrubbing factor table on the right-hand side, it's a factor of 1. Okay, so we use this table on the right-hand side to work back to our nameplate capacity scrubber when we're at lower carbon dioxide levels. Okay, so let's work through an example here to understand how to size a scrubber for our complex. So let's build a new complex, 8 rooms, 1,000 bins per room. Let's plan to store at 1.5% carbon dioxide. So what do we need to do to figure out the scrubber? We need to calculate the amount of apples we've got in the complex, and we need to calculate how much carbon dioxide these apples are producing. So let's use a dimensional analysis, do the maths and multiply out. We've got 8 rooms multiplied by 1,000 bins, multiplied by 380 kilograms in a bin, and we see we've got a whole lot of apples in our complex. So we've got all these apples in our complex now. How much carbon dioxide are they going to produce? We need to use the respiration rate of the apples. So we take 0.066 kilograms of carbon dioxide per kilogram of apples, multiply it by all of our apples, and we see that our apples will be producing 200 kilograms of carbon dioxide. So we need to manage this 200 kilograms of carbon dioxide that our apples are going to be producing in a day. We need to match the scrubbing capacity to remove the CO2 that's being produced. Okay, so we know that we're storing at 1.5% carbon dioxide, which is below the nameplate of our scrubber. So we need to apply our scrubbing factor to determine our nameplate capacity. At 1.5% carbon dioxide, we need more scrubbing capacity, and that makes sense here. We look on our table and we see we need to apply a scrubbing factor of 2. So the 200 kilograms that we're producing, we multiply by a factor of 2, and we see we need a scrubbing capacity of 400 kilograms, which is obviously more than the 200 we're producing because it's harder to remove carbon dioxide at lower concentrations. So the 400 kilogram scrubbing capacity gives us an IS 400 scrubber. The 400 nameplate of the IS 400 matches the 400 scrubbing capacity that we need. So we can use the table of our scrubbers as well to double check that we've done our maths right. So at 1.5%, we read across our range of scrubbers. We try to get away with the smaller scrubber we need to manage the 200 kilograms of carbon dioxide that we're producing. So here, 200 kilograms, we read up, we see it's an IS 400 scrubber. We're only at 1.5%, so this 200 kilograms is what will be removed by our IS 400 at 1.5%. Okay, so let's just go back and look at some notes on respiration to support our calculations. We've used 0.066 kilograms of carbon dioxide per kilogram of apples per 24 hours at 0 degrees. Now that sentence is really is a mouthful, but it's important to take notes of all the various units here. We've got kilograms, we've got 24 hours, and we've got 0 degrees. Various publications and reports will use milliliters, could use moles to quantify the amount of carbon dioxide. We can also talk about hours instead of days, and also might not all be at 0 degrees. So let's bear that in mind. Why is the temperature of 0 degrees important? Because at higher temperatures, we know we've got a higher respiration rate, and the carbon dioxide produced will increase. And a rule of thumb is fruit at 21 degrees will produce 7 times the carbon dioxide as fruit at 0 degrees. Imagine doing something 7 times over. So why am I harping on about temperature? Why is this relevant? Because we do stepwise cooling. So we might have periods where our fruit is not at 0 degrees. Not all of our varieties or cultivars are stored at 0 degrees. And we're also loading our room with fruit, warm fruit from the orchard, and sealing our rooms before the room gets to 0 degrees. So it's important to bear this in mind when you're doing your calculations. Okay, so in the previous example, we chose our IS 400 scrubber. We've installed it for our 8 rooms at 1.5% average CO2. So let's look at how storing of different varieties will impact our carbon dioxide management. So for this example, let's decide to load 4 of our rooms with Goldens at 2.5% carbon dioxide. And let's put Pink Ladies in 4 rooms and store them at 0.5% carbon dioxide. We've still got an average of 1.5% carbon dioxide, like our previous example. But remember, we've got these 4 rooms of Pink Ladies that we're storing at 0.5 CO2. So, and we know that at lower carbon dioxide levels, we need more scrubbing capacity. So let's remind ourselves on our table about how our scrubbing capacity decreases at lower CO2 levels. Our IS 400 scrubber, if we now look at 0.5% CO2, will only be able to scrub 57 kilograms of carbon dioxide out of our room. In the previous example, we're producing 200 kilograms. With 57 against 200, we can already see how we might have an issue. If we look at our scrubbing factor table as well, at 0.5% CO2, we need 7 times scrubbing capacity. So we need a lot more scrubbing capacity than we do if we're storing at these higher levels. Okay, so let's tackle this second example by variety. We've got our 4 rooms of Goldens that we're storing at 2.5% carbon dioxide. These 4 rooms of Goldens will be producing 100 kilograms of carbon dioxide, half the amount that was produced in our previous example because it's only 4 rooms. We're storing at 2.5% carbon dioxide, so using our table, we know we can multiply by 1.2 to see our nameplate scrubbing capacity required. So we need 120 kilograms to manage our golden rooms. Looking at the Pink Ladies that we're storing at 0.5% CO2, 4 rooms. These 4 rooms are also producing 100 kilograms of CO2, the same as our Goldens. So same amount of carbon dioxide to manage in these rooms, but because we're at 0.5% carbon dioxide, we multiply by a factor of 7 to account for the difficulty at that level. And we see we need 700 kilograms scrubbing capacity just on our Pink Lady rooms. So across our 8-room complex now, we've got a total requirement of 820 kilograms scrubbing capacity, and we now need an Eco 850 scrubber. So double the size of more than double the size of the 400 scrubber in the previous example. So let's just go through both examples side by side quickly to make sure we haven't tricked ourselves or made any mistakes. So we've got both examples. We've got 8 rooms with 1,000 bins. Both examples, the apples are producing 200 kilograms of carbon dioxide a day. And they're both at the same average of 1.5% CO2. But in the second example, we need double the scrubbing capacity. And that's because of our 4 rooms of Pink Ladies that we're storing at 0.5% CO2 and the difficulty associated with removing something that is rare from the room, the lower carbon dioxide concentration. So what have we learned from that example? We've learned that we need to plan ahead. We need to work out our scrubbing capacity that we need per room. We needed, in the previous example, we needed double the capacity. So don't load all your low CO2 rooms on the same scrubber. And also beware of warm fruit and the associated higher carbon dioxide production that comes with it. So let's plan ahead. We've touched earlier on efficiencies in the talk about motors and about electricity and batteries. And we have the same efficiency considerations we can take into account with our scrubber. What if the carbon in our scrubber isn't efficient anymore? How do we account for that? What do we need to do? So I'll show you on the next few slides how we account for the efficiency of our carbon and how we test for that. So remember, our scrubber is filled with a special activated carbon, which absorbs the carbon dioxide from the room. And this carbon, we should consider it an engineering component, which can degrade over time. And that's roughly about 12,000 scrubbing hours, over which you'll lose your capacity to absorb the carbon dioxide from your room. Okay, so how do we test? How do we measure to see where your carbon efficiency is at on your scrubber? So we connect an analyzer to the outlet of the scrubber to measure the atmosphere going back to the room. And we get a performance profile that you can see in this green curve. So in this example, we've got our room at 1% carbon dioxide, as shown by this blue line. And we're measuring what's going back to the room. So you can see here, this is a good performance curve on one cycle, on one drum of the scrubber. And in the beginning of the cycle, you can see there's no carbon dioxide going back to the room. We're removing all of it. So the scrubber is really performing well in the beginning, but during our cycle, the carbon saturates. And that's why we've got 2 drums and 2 blows in our scrubber. So we can switch over. When this drum is saturated here, we end the cycle and we jump across to our other drum that we've just regenerated, and we can get the same performance profile of that drum while we regenerate this drum and remove the carbon dioxide from it. So how else can we interpret this graph? So let's consider the area under the curve. We said it's carbon dioxide going back to the room. We want as little carbon dioxide going back to our room for our scrubber to be the most efficient. So the area under the curve here in green can be thought of as the physical kilograms of carbon dioxide going back to your room. So naturally, you want this area to be as small as possible. So if we hook up our analyzer to a scrubber with carbon that's degraded, it's done its 12,000 hours, it's removed all its CO2, it's now inefficient. This red curve will show what we expect to see. So quite easy to tell. You can see the performance profile of the green curve here and how much bigger the area is beneath the red curve. And you can see it's about 20 to 30% difference between the two. So if you were short on scrubbing capacity beforehand and your carbon is now inefficient and it's degraded over its lifetime, you can see you'll be further short of scrubbing capacity. So in conclusion, what have we learned today? Using an average carbon dioxide calculation for our complex might not always be sufficient. We should probably consider calculating the scrubbing capacity required on a room-by-room basis, considering what varieties we're storing in there. An easy rule of thumb is not to load all your low carbon dioxide rooms on the same scrubber. And the efficiency of our scrubber carbon, we should check it roughly every 12,000 hours. That's quite easy to do. We just connect the analyzer like we saw in the previous example. So it's very important to plan ahead. It's important to know our rooms, what cultivars you're going to be storing, at what set points, and also to know our equipment and what their capabilities are and where they are in their life cycle. and we can help you with that. So get in touch with us, and if you're struggling, we'll help you understand where you're at. Thank you for your time. If there's any questions, please shoot them through.
Good. Thanks, Josh, for informing us on the scrubbing capacity. This is not a test your maths question, but many people are storing Pink Lady at 1 degree C, and together with the low CO2 of 0.5%, how does that change the factor in terms of scrubbing?
Let me quickly just jump back. I don't actually have the slide here, but we know, I spoke to Alka about it yesterday, and Dr. Bob Krang from Canada, and we know the rule of thumb for respiration is respiration rates double every 10 degrees Celsius. So if we're at, all our calculations are done at 0, so if we're 1, 2, 3, we know it's exponential between 0 and 10. There's not a lot of research done on specific respiration rates at 1, 2, or 3 degrees, but if we just interpolate, we can look at about 20 to 30% more respiration at 3 degrees. At 1 degree, it'll be a bit less, but that's why it's important just to bear that in mind, and we can't just rely only on our calculations. We need to understand where they're coming from and account for that.
Thank you. Are there any questions for Josh?
If you've got no questions now, it's a bit more complex because you've got a whole lot of rooms or whatnot, you're welcome to either give me a call or pop us an email at Gas at Site, and we'll be more than willing to help you figure out where you're at. Okay, so you can contact Josh at any time. Are there any specific questions at the moment?
I've got a question. Sorry, okay. You broke up just now, so sorry, I couldn't hear everything, Josh. My question is more related, how does one calculate, the scrubbing is really important in the beginning, and later when you store at low temperature, then the scrubbing capacity has to be lower. So it's a bit like Marius's cooling question, where he said like you need 60% of the total capacity. In this case, it's not like that, because if you don't bring down the CO2 in the beginning, you're going to have problems later on. So yeah, so it's kind of complex because you have to move from a high temperature to a low temperature, and yet that is kind of actually a very short period of time during the whole storage time. You can't get away with getting a smaller CO2 scrubber because the beginning is actually quite important. So it's kind of a question and a statement. I'm not sure. What are your thoughts on that?
Yeah, Alka, thank you. Thank you for that point. So luckily, in a CA complex, we've got quite a few tools that we can use to help us. If we've got warm fruit going into the room, we don't have to seal the room immediately. We can leave the door a bit open. We've got our fans on while we cool the fruit down. So if the room isn't sealed, we won't have that buildup of carbon dioxide. The door's open, we'll be blowing some of it out with our fans while we cool down to our lower temperatures. And then also we're pulling down the room with our nitrogen generator. We're blowing down the room with nitrogen to displace oxygen to get to our set points. But the nitrogen generator will also blow off the carbon dioxide in the room. So that also helps in the beginning just to knock those CO2 levels down when we're at higher temperatures.
Great,
so you've got those tools, so you use them to your advantage. Because if you had to size your scrubbers for that peak CO2 production in the beginning,
it won't make it.
It wouldn't make economic sense.
Oh, great, thank you very much. That's a good one.
Good. Any more questions? Okay, doesn't look like it. Thank you, Josh. Thanks for your presentation.
Thanks, Richard. Thank you.
Yeah, we're at the end of the presentations. We're now going to move into the meeting component of today's webinar. And so people who are not involved in pack sheds are welcome to leave. But I think we need to talk about whether this type of webinar is successful or not, whether we should repeat it. We've had presentations that spoke about general packhouse issues, and others more specifically about CA storage. So is it a CA engineers meeting, or is it a packshed engineers meeting? More I would call it a packhouse action group engineers meeting. These are the type of things that I would like some feedback from you folk. It'll help us just to plan the future, as to what we do next year this time. So, en julle kan nou Afrikaans praat mense, so sê asseblief julle sê. Can I have some comments, please? Just unmute your microphone. While you're thinking, I can just say to me, the registration indicates that there is a definite demand for this type of seminar. So we will also obviously discuss it in the Packhouse Action Group as to how to take it forward. But I would appreciate your comments either now, or you can send an email to myself or Tia, and we can take it from there. We have a Packhouse Action Group meeting again early in August. So then we can talk about it. But are there any comments at this stage? We did receive a question here from someone. It's just a question which I'd like to ask the group, which I don't know the answer of.
What are the pros and cons of deconditioning of a CA room before it is to be opened?
What are the pros and cons of decommissioning a CA room? Deconditioning a CA room before opening. Can anyone help with an answer, please? Perhaps the person who asked can explain what he means by deconditioning.
Yes, I think the person mean that to get that room back from the controlled set points to ambient temperatures and gas levels. If you open your big door, if it's possible to open your big door, you should be back to 21% oxygen within 45 minutes. If you just open your small door, it'll take longer, around about an hour and a half, for your room to get back to 21% oxygen. If I could add that.
Thank you for that explanation. Are there any other comments? You're welcome just to put them on the chat as well. Oh, there's a question. Can you please give me permission to record the session? The session has been recorded. That will be made available with the presentations.
Yeah.
But if you've recorded it, then you've got our permission. That's fine. Thank you for asking. But there will be a recording available as well. So everyone happy? Well, I think we've had a good session. We've had some very interesting topics. We in fact had more topics than we had time to accommodate. Some of them we will be looking at accommodating in the post-harvest symposium in November. So what we could not include here, we will try and include in November. So that will be in a symposium webinar format. But then the question is, I think what you can also do is just throughout the year, email us and say, you've come across this technology, it would be useful if it could be shared with all the participants, and then we could invite a person to speak on that. So that'll help us greatly in servicing your needs in terms of advising you on new technologies. I think that's really what it's about, is to expose everyone to new technologies that can make a difference to your pack house. So if there's no further comments, then I'd once again like to thank the presenters again for their presentations. Thanks for all the participants for taking the trouble to spend the time with this webinar. And final thank you to Tia for doing all the administration. Thank you very much. So thank you, everyone. And we're now going to close. Thank you.
Thank you.
Good.